Hello all, hello all. Hello all. Hope you all can see me and hear me. Let me know. Everything should look good and sound good, right? Yes, let me know. Hi Jerry, I see you. Hi Mike Richardson, I see you both. Obviously the Purdue game must not have gone all that well. Otherwise Jerry wouldn't be here right now. Hopefully everybody is doing well. I see lots of people. I see people from Boise, from Idaho, from Germany. Thank you. Southeast Australia. Thank you so much. Good to see you all. 5x5. Awesome. Love it. Love it. My audio's loud enough but not distorting, and my video looks good. Wonderful. So hopefully you guys can all see yourself here in the chat. I've got another version of it that I can see. I know it's kind of hard to see here, but I'll make sure we have a nice slide to go to that's empty. Okay, I'll go to that slide later. Actually, I'll go to that right now just to say hi to everybody. Oh, that's not really empty, is it? There you go. There's an empty one. Hi, all. Good to see you all. Okay, so I will get started here. There's a couple little caveats I want to say right away. If you hear noise in the background, it's because we actually have some people doing some plumbing. We have a clogged line. So so if you hear weird noises in the background, it's okay. Just having a little work done. That's the first thing, and then the second thing is that this is the second installment of a course, or a set of courses, a series called the D series, which I have to make more visible on YouTube. Some people have let me know that they're kind of hard to find. I need to put them back on my front page. So I will start a new series of courses that you can find on the front page that is probably specialty courses or courses about data products. So this will be probably about a 5-course series on exactly that. And the very first of these, and I'm going to go to the title page now. The very first of these that we had just about 2 months ago, we didn't get through. We're just basically going through the basics. Okay, so all of the data products that you see on the SWPC, the Space Weather Prediction Center page, we're going through a lot of those. I will pull a few in this time that are slightly off topic, that are off not off topic, off SWPC's page and into a realm of a few other places, just because they're really important in terms of looking at basics and being able to pull them together. So I'm hoping we're going to get through all of the basics today. If your specialty product that you love is not on here, it's probably because it's more advanced, and we will get into it, because after I get through the basics and I give you the fundamentals of what we're doing, basically of what space weather data products are about, how they work, why we use them. Once I give you those basics, then we can build on them. And so what we'll do in subsequent courses is that we'll go back to some of the basics, and then I'll pull in other ones that are more advanced and show you how they interrelate, how they are better, how they are worse than the basics, and where you can find them, and how you can utilize them to the best, to give you the most insight into space weather phenomena as they are occurring or as they will occur. Okay? So hopefully that makes things clear, and I'm going to take the chat off right now. I'm glad everybody is doing well, and that this stream looks good. So let me make this clean, and I will do my best not to be distracted, as there's a lot of heavy machinery just outside my window here. Okay, come on. I don't know why my camera isn't focusing. Okay, so as I do always, I like to make sure that I give credit where credit is due. I have my VIP steering committee and my standout members up here who really talk to me on a very deep level and really offer their insight and are supporting me at a very high level. I appreciate you all so very much, because without you I couldn't do this. And then of course this whole group of people, these are the people that steer the ship. You might think that I just do whatever I want in this space weather woman endeavor, and I don't. It's actually ruled by committee, and all of these people have contributed so much to whether or not I succeed, and really where I go from, in terms of content, in terms of talks I give, things I focus on, data products I create, stuff like that. So as the machinery kicks in. So I appreciate all of these guys very much, and if you are interested in joining the VIP committee, please come to my Patreon website and have a chat with me, and we will see what we can do. And now, of course, everybody who gives me, who supports me at the mini course, the Q&A mini course tier, you all are the ones that tell me what I should do next, how to do it. I've got a couple questions, for instance, that I will answer today, even some new questions that I didn't answer during the very first D course, and during D1. I didn't have a couple questions that people wanted answered, so I'm inserting a few things in this particular mini course so that you can see that. And these are the folks that help me do it, right? So I listen to every single one of these people, and I'm sometimes a little slow to answer just because right now it's solar maximum and I'm tugged in so many different directions. But I do respond to you, so please feel free to reach out to me at any time. Okay, so this set of mini courses, right, is really to help you understand how to look at my forecasts, look at other people's forecasts, right, look at the Space Weather Prediction Center page, and really make sense of the data products there, and be able to make sense of them in the proper way. There's a ton of people out there that try to understand these data products because they're publicly available, right, and they have some level of description of what they are. But to be honest, the devil's in the details, and I see more often people on YouTube and on social media who are not skilled at this stuff, who are not formally trained and do not know the data products like they think they do, and they'll point to things that they shouldn't, and try to say that it explains certain things that they really don't. So I'm hoping that this will help set a lot of things straight for everyone. And if you ever, and of course these YouTube mini courses are always archived, they're always here for you. So anytime you need them, you can go back in and search for them. Eventually I'll get things archived or things annotated in the index so that they will be, so you can look at the different data products that I address. I might need help with that from some folks, but I will do that for you because I think it's super important for you to be able to very quickly access the different data products that are available for you, okay? And also, before we get started, Jerry and Mike, they are the moderators of this. You also see them up here, Mike and Jerry. These are the moderators of this, of my YouTube channel, and so they're the moderators of the chat today. They will keep you on topic. If you have burning questions that are slightly off topic, I'm sure that's fine. They're not going to, be extremely rigorous, but they might ask you to hold them till the end or till a break, so that the conversation in the chat stays on the topics that we're currently discussing. Okay, but don't feel like you've got to not ask anything that's slightly off topic, but just not stuff that's right way off topic, because it is a distraction to others here who want to learn. Whoops, what happened? Okay, that was weird. All right. So without further ado, let's talk about a little bit about what we did last time, right? We actually got through about 40 charts last time, which is pretty good for us. Let me make this big. We actually got through a lot of them. Now, again, as I said earlier, I'm only doing a small subset of products. There are a ton of data products out there, and if those of you who actually have access, for instance, to the ESA web portal for space weather products, they're adding stuff at a momentous rate. It's insane how many data products that are in there. That's a password protected thing. You have to actually get an in-action account to see those data products. But there are so many of them. And I won't be going over, obviously, all of those. A lot of those are actually advanced products. So those are things that we can go over later. Right now, I'm staying mainly with the SWPC Space Weather, the Space Weather Prediction Center page, or SWPC as we call it, that NOAA puts out. And those, mainly because those are easy to access. They're, the Space Weather Prediction Center was the first space weather center It used to be called the Space Environment Center, SEC, and then it was called something else before that, which I forget. It's been around for a very long time, and so it's the most well-known, and so it's obviously one of the most robust sites out there. And so their data products very rarely go down. The website very rarely goes down, and which is great because we need this stuff all the time. And other sites have a tendency to go down a bit more. So that's why I'm focusing on that. Plus, it gives you the good basics. And we went over solar imagery, interplanetary space inside the near-Earth system. Right, so we're getting into the second chef, which I'll talk a little bit more about later, probably a different mini course. But we have yet to go through the ionosphere and the ground level. So again, these are the ones that we just went through in the last course. I will give a slight review of these, but I'll also talk about the ionosphere ground level, and I'll also add a little bit about the solar cycle prediction stuff. This was like sunspot number and F10.7 over the course of the cycle. I've had a couple people ask me about that, and so I thought it was important to add. And then I will also at the end, just because we're going through the basics doesn't mean I'm not going to demonstrate a little bit about how these basics can actually be used in a very advanced way. And how you do that is by combining them. Okay, you combine multiple basic data products together, and what you can get is a lot more insight into the space weather phenomena, and that's really where the basics have a lot of power. Okay, so I will talk about that now. It's not going to be exhaustive, right? As long as you understand that there will be things that we will miss. And so I'm going to start. Let me start a quick review. Okay, so I've got like 20 charts to go through, like lightning fast. And the reason for this is because all of this is in the D1 mini course. I just want to kind of give you a heads up and kind of remind you, get your feet wet because it's been a little while since we chatted. Okay, so the Space Weather Prediction Center page looks like this, right? This scrolls down, and then you can see what the bottom 3 panels here or the top 3 panels here. So the site continues to go down. I don't know why this didn't fill out all the way, but hey. Anyway, you can see imagery from SUVI. You can see coronagraph imagery. You can see the Ovation model on the front page. You can see X-ray flux on the front page. You can see radiation storm or solar energetic particle event stuff on the front page. And then you can see KP, right? Those are the basic data products that they have on the front page because those are oftentimes the ones that are accessed the most. But if you go to products and data, here you can find really everything, okay? And so last time I would go and I'd do live stuff and I'd click and show and click and show, and I can do that again. I will do that again here and there because it's much more conducive to do it live. And if you guys, feel free, if you guys happen to have 2 screens or whatever, pull up the Space Weather Prediction Center page. Okay, I don't know if I have I probably had it last time. You probably can't see it here, but I will make it big. Hold on. I should have put a big link. Come on. Oh, I don't know if you can see that. That's as big as it's letting me go forward right there. Okay, so swpc.noaa.gov. And if you want to pull that up, right, so then you can have a working copy of it and look at the data products as we go along. Okay, there'll be a couple places where that's going to be a little bit, where we change data sites, but for the most part, we're going to be here. Okay, so if you go to the products and data page, you will pull up all of this. And like I said, last time we went through quite a few of these, not all of them, but quite a few. So talking specifically about solar imagery, right, or on-disk analysis, meaning on the disk of the sun. Some people say, why do you call it a disk? Well, it's because when you look at the sun and you have this integrated line of sight, what you see is a flat 2-dimensional circle, right? And so that is not, you're looking at a 3-dimensional surface that's flattened into 2 dimensions. And so it has, especially near the limb, where everything begins to go to the kind of pointing in a sideways direction from you. If I grab, where's my ball? Oh, there it is. Right, if you see this ball, everything here on the side, on the edge of this ball, right, that becomes a problem to see because it becomes, you have to see like from here to here. That was actually that was almost a quarter of the sun. But to you, it looks like just a few degrees. It looks like just a tiny movement. It's actually quite a bit of a movement. So you get a lot of squishing of information as you move to the edge. And so it's not really a round thing, it's a flat thing. And it kind of reminds us that, at least as scientists, that it's a disk that we're seeing, right? It's not the full edge of the sun. And no matter where you are, if you are looking at the sun from a different angle, it's always a disk that they see, and it's a different disk that they see than that you see. So we typically call it a disk. That's one of the reasons why we call it a disk. There's all sorts of other reasons too. But that's my favorite way of thinking about it, so that it always reminds me that on the edges of the sun, right, where we always say, well, why does all of the solar events seem to happen far more often on the east limb or the west limb? Well, that's because you're seeing a lot more of the sun on those edges than you are in front. Right? In front, you're seeing about 60 degrees, and then it go to the edge, you're seeing a whole nother set of 60 degrees. You're seeing a whole nother huge swath of the sun that's all kind of crushed together because it's foreshortened. Right? It's all, you're seeing these what we call limb effects, and that's why you see limb brightening. You see all these other types of things, and that's why we can also see occulted flares. Right, where an active region is actually sitting on the far side of the sun, but we still see the flare kind of peeking up from behind the limb. And that's because there's really a lot more surface area that we're seeing around the corner that still makes it to our view. Okay. So it makes it seem as if things are occurring on the east and west limb a lot more than they do. It's really because we just don't see that much. Okay, here's SWPC. Right, I talked about this before. I won't take the time to go to a live view of SWPC, but if you go to the products and data, you can go to this imager and you will get lots of good stuff. I talked about it back in last course, and this was what SWPC looked. This is what 171 angstroms looked like back when the sun was quiet. I miss those days actually. It's too busy right now. It's too much of a mess, and it's going to get messier as time goes on. Here's a similar image for Solar Dynamics Observatory, right? We're looking at the AIA instrument, not the same wavelength. This is actually 193, or 193, which sees coronal holes. 171 does not. Again, this was during solar minimum, so we had nice, well-behaved coronal holes that were up at the poles. Now they're kind of like in this layered, almost spiral-looking thing. It's a mess. And again, it's going to get worse. We're going to get more coronal hole influence here over the next couple years, which will make forecasting a lot more fun. But you can get data for imagery from the SDO, AIA archive, as well as other HMI archive there. We also have coronagraphs. This is amusing to me. There's nothing. Doesn't look like today. If you go to the coronagraph imagers today, there's a lot more going on. But again, this was 2020, right? We were just coming out, trying to squeeze out of solar minimum. So we had nothing going on. C2 field of view, C3 field of view, they're always colored red and blue, at least in their raw imagery, to help us see. Of course, you can always tell which field of view you have by how big the occulting disk is, and of course how big the sun is. Okay. All right, C3 field of view is out to 30 solar radii or 15 sun lengths, and C2 field of view is out to 6 solar radii or 3 sun lengths. Okay. One of the things that I also talked about is seeds. Seeds, I think I talked about cactus as well, but seeds is one of my favorite because of how it does its graphics. This is an automated algorithm that then tries to capture coronal mass ejections in coronagraphs, and then does some an analysis of the bright fronts and the dimming in the core, that kind of thing. I think it just uses the bright fronts, to be honest. And it tries to estimate what the speed would be, what the position angle is, how fast it's moving, all of that kind of stuff, to give you more details about the actual event. And it shows raw imagery and it shows difference imagery, which is one of the reasons why I like it as well, because it allows you to see both, and that's always important. But as you can see, here's some couple red and blue lines here that kind of show you where it's catching the front of this structure. If the structure's too dim, it won't capture the whole thing. Like you can see some stuff out here. It's not capturing that. None of these algorithms are perfect, but they do capture things reasonably well, except here, right? But it allows you to see things a lot better if I stand out of the way. And it's just a nice database to see if you can catch things and then annotate and put in tables where these big coronal mass ejections occur. Again, they don't get everything. I think here I was showing examples where they don't get everything, but we talked about it more in detail in the D1 course. Another great one is looking at the Space Weather Prediction Center. Can I make this loop? I don't know. Can I make it loop? Well, that's interesting. I don't know why it won't let me make it loop, but all right. But you can see kind of some of these images. These are the synoptic charts, and I believe I went over them reasonably in detail last time, where you can see everything from little coronal holes to active regions. Let me do one if you've got one in color. These are written every single day. I like Spencer. He does a great one because he does it in there. There's one that's colored because he does it digitally. Each forecaster does them differently. But what's nice is that they not only show you the numbers of the sunspots, and here's a great place to go to ensure that you have the right sunspot number if you're labeling sunspots or you're trying to find where a flare might have occurred. But then they also have these numbers under here that show, whoops, under here, yeah, that show basically this chart for each one of these active regions. And it's really the percentage of percent chance you're going to see C-class flares, M-class flares, X-class flares, or a proton particle radiation storm. Okay, so that's what you're seeing in here when you see these numbers. I talked about coronal holes as well, and what you see with the quality flag as well as the polarity. And I'll talk about the details of these things more as we get into more advanced topics and we talk more about the Russell-McFerrin effect. But these are very nice because they show you polarity, inversions where you're seeing where the different fields are. You're seeing, of course, the polarity of the coronal hole, which matters as to whether or not something is going to be geoeffective. And then you see things like filaments where they might be, that type of thing, prominences where they might be, okay, and all sorts of other good stuff. And I'm sure I went over all of this. I hope I went over all of this. But that's just kind of a record of letting you know what image they were looking at in what wavelength of light to create this kind of this overall, composite view of all of the different features of the sun for that period of time. Okay. Other things I went through was the difference between white light and looking at magnetograms. Magnetograms tell you so much more. I don't typically look at white light, to be totally honest. I'll look at them sometimes when I can't quite figure out what the heck is going on down here or why something has not been numbered. When I see a region that looks like it should have a number and I go to a synoptic chart and I don't see a number like the charts I just showed you, and I'm like, why isn't it numbered? Then I'll flip to a white light diagram to say, isn't there a spot that's visibly on the disk or not? But that's about all I ever use white light diagrams for. Outside of that, I really do stick with magnetograms. And the reason for that is because, you get a lot more information. You get a lot more information, not about just the umbra and the penumbra, right? But you get information about the magnetic polarity. You get information about where the neutral lines are, where flux may be emerging even before you see it. In a white light diagram, you can see flux emergence. You can't always see it here, but you sure can see it on these diagrams, right? And I'm sure I went over I know I did. I went over all the details here because we talked about the different classes. Now these are useful to know. I'm including them in the basics because a lot of places show, right, the reading of these structures, right? These beta, gamma, gamma, beta, delta, beta, gamma, deltas, blah, 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 right? And what you're looking at in this, just as a quick refresher, this is white light. This is what it would look like in the magnetogram. So in the white light, you're just looking at sunspots and the type of sunspots. Some of them will be these tiny little things that don't seem to have a penumbra. Some of them will have penumbras, right? For instance, when you see an alpha compared to a an alpha in magnetograms, you'll just see a polarity because they're both the same polarity, right? So that you might not see the umbra, which is the black, and the penumbra, which is the lighter, still dark, but not quite as dark, right? Ring around these spots. In magnetogram, you may not see that. Okay. It's oftentimes nice when you do imagery if you overlay the two, which is what you oftentimes see. I'm not going to show you an example of what I do, but sometimes you see that in my forecasts. I'll have a white light. You'll see the umbra and penumbra kind of sticking through this, the magnetogram, but I always highlight the magnetogram because to me it's more important. But at any rate, we use the umbra and the penumbra in order to get these classifications. So here's an alpha because it's a single polarity. Here's a beta because you've got a nice simple neutral line, right? And you've got a polarity inversion. And it doesn't matter how many spots you have inside if they're all the same polarity. Okay. Here's a beta gamma. And the reason for that is because you've got more than one neutral line. It becomes complex. It's not just a big alpha, a big beta. You've got actually multiple neutral lines in here because if you go from black to white, you're going to have a neutral line in the middle. Here's white to black, you got another neutral line, and black to white, another neutral line. Okay, so it's a complex spot or complex cluster, right? Here's also a beta gamma, again, because you've got multiple neutral lines. Now you got lots of neutral lines. But in this case, if you look at the white light diagram, none of these polarities that are opposite, right, because you get black and white are opposite, these are opposite polarity from this big spot here, but they're not sitting in the penumbra, which is the reddish region. They're not incursion, you're not having an incursion into that penumbra. So we don't have delta spots yet. Okay, this is just a beta gamma, right? And this is a gamma in this case because we don't have really a nice organized beta spot. You know, you don't have big ones in here that have a nice big dominant neutral line in there. You just have a bunch of like little tiny clusters. So it's just a gamma. But then when you start getting reversing polarities, right, so you can see these still look exactly the same. But in this case, one of those little spots, this little guy actually has the opposite polarity. Well, that's where you get the delta, right? Same thing here. You've got a beta, looks exactly the same in white light, but in magnetograms, this little spot is the opposite polarity, and it's in the penumbra, so you're going to have a delta there. And the same kind of thing goes. Anytime you have a delta spot, or anytime you have a spot of a different polarity incurring, barging in and crossing over into the penumbra of a different polarity, which is shown here, you're going to have a delta. Okay. Same thing here. In this case, you don't have a nice beta, right? You don't have a nice set of beta, like a nice polarity inversion. But you do have an umbra. See, like there's nothing pretty here. It's all kind of complex. So you don't have a beta in front, but you do have this penumbra. And in this case, these two spots, as you can see from here, these two spots have the opposite polarity. So you do have a delta. So in this case, it's a gamma delta. Okay. So you can use these in concert. I still, for the most part, stick to this because I'm not trying to label these regions. I just look to see what the complexity is. And of course, delta spots obviously are, when you start getting those, you almost immediately know you have X-class potential, almost immediately. It depends. Sometimes with a gamma, if they're really small spots, you may not have X-class potential. But if you have any big leading spots, anything that looks like a beta, and you start having deltas in there, that's a big flare player, okay? All right. Just making sure I got a notification on my phone, so I just want to make sure everything's cool. And why did I take the time to do this, even though I had already talked about it in last class? Well, it's because so many people use Space Weather Live, right? And these guys are fantastic. We even in Millersville, Mike Cook even teaches using Space Weather Live. I still teach mainly using SWPC because I want people to get the basics, but as you get more complicated, then Space Weather Live is really, really good. Plus, they have a wonderful archive. And their tools are a lot of times much more intuitive. Okay? So like here is an example of a sunspot that they've gotten. You could slide this little bar back and forth to kind of go back and forth between the white light and the magnetogram. And you'll see lots of information about the sunspot regions, what the numbers are, and what their classification is. You can see them here. Right, and they'll label them green, yellow, red, right? So they make them stoplight. So for instance, here is a beta, gamma, delta. And so it's a dangerous region, which it was. I can't remember how many flares it fired off, but, and they even give you a flare class down here, the potential to fire off. And I don't know if these are consistent with SWPC or if there's a lot of different sites and a lot of different data products that have their own flare classification potentials for each spot, and none of them ever are 100% similar. I don't think I've ever seen two that are completely alike. I stick with the SWPC ones simply because I'm in the United States, and right, they're the oldest and most well-known prediction site out there. So I stick with theirs because they're also the official for the United States, so it's a good reason to stay with them. But again, Space Weather Live tools are fantastic, and they give you new insight, and they give you different ways of looking at the same data. And I'll return to Space Weather Live. And literally it's spaceweatherlive.com, right? Really easy. Okay, another thing we looked at together was X-ray flux. And I love the contrast. Here's the X-ray flux from solar minimum, right? Was this 2020 as well? I see August. Where is the date? Oh, there it is, down there. Yeah, 2020. So this was 2020. Look how quiet we were. We were sitting below the or almost at the A floor. Do you see that? I mean, that's what a difference a day makes. Right now, our noise floor is sitting up in between C and M, typically. So it shows you how radically different we go from solar minimum to solar maximum. But we talked about that, and I will talk more about that today as well, because we have things to discuss. All right, I also brought up, and when we got to interplanetary space, I talked about ENLO, okay, and I even showed you the ENLO model run for the May event, and we'll show this a few times, not just this event, but we'll return to the May event for multiple data products. And you can see, again, look at all the events that came out all at once. Not all at once, but rapid fire. That's very common with these big bad actors, is that they just keep firing. They show up on the disk, either emerge or rotate into Earth view, and they are so upset, and they just keep firing. They just keep reloading the gun and go over and over and over again. And so we had that gorgeous G5 storm. The barely G5, but it was a G5 back in May. Okay, I went over that. I went over real-time solar wind from, in this case, Discover, or sometimes even ACE, and you can tell which is the active spacecraft by looking over here. Discover sometimes has issues with its data because it has its plasma Faraday cup has a problem with a ground wire. So sometimes we will switch over to ACE data, and so you will see when that happens, and at the bottom of the data set, which I'm not showing here, but at the bottom of the data set you can actually see where the data is untrustworthy or where they switch, what is the active spacecraft. You can get all sorts of data there. But I talked about the magnetic field direction in Cartesian coordinates, right? And then I talked about the angles. And I might even have, oh, I think I took that out. I actually did end up correcting the angles in my chart, because I remember I had the angles wrong because I grabbed I just grabbed a chart, a definition off the web, and they had theta and phi symbols reversed. So I kind of laughed at that, and I actually corrected that, but I don't think I'm going to show it here. I can go over that during our Q&A if you'd like. But here are some examples. I even went over some examples in the interplanetary medium, and went over some of the details. I think, do I even have the other? Yeah, you can see here, as the storms unfolded, I talked about a little bit about how you can actually predict when you've seen just a very small portion of these coronal mass ejections. You can actually predict what their signature is going to be if you're in the solar storm core. I don't think I went through the actual process of that, and there's a reason for that, is it takes a long time. But I've already done that in a previous mini course. If you go check, I think it's the C, is it the C series? And because that's for coronal mass ejections. In the D1 course, I actually put that up. I actually put up a frame and showed you the link, showed you which course to go to for that. But you can actually learn how to predict what these structures are going to be. For instance, this structure, if the white is BY, which it is, this is west and this is east. It crosses through 0, so this is west-east. And then this is your BZ component, which is fully north. So this is a west-northeast rope. If I had seen just this much of it, I probably could have predicted that it was going to be west-northeast. So you would have had a whole another, 10 to 12 hours where we would have known we wouldn't have gotten really much storming at all. So you can predict early on what both fizzles and what really strong storms are going to be, simply because you recognize that it's a solar slinky in the core and you can predict its magnetic field orientation. Same thing with this one. In this case, oh, what is that? Is that B? That's BX is yellow, BY is blue. And do I have BZ? Where's BZ? My goodness, I can't even see it. BX, BY, where's BZ? BZ's red. Yeah, so this looks like yet another one. Boy, these things are really dim. I'm looking at my monitors on the side here. So blue goes down, so that would be east, west, and then red is north. So 2 fizzles. So this is an east-northwest rope, sadly. So I didn't show really good ones here, did I, for storming? But nonetheless, you can do these predictions, and I gave you good ideas as to how to do that. Okay, let's jump inside the near-Earth system. We're still doing review. And talked about magnetospheric movies, right? And I think I dispelled the idea that solar wind does not go backwards. When you are in the Earth's magnetic system, if you see a velocity flow going toward the Earth, those are bursty bulk flows. We are inside the Earth's magnetic system, which means we are inside the near-Earth skillet that scrambles everything up. This in here is not solar wind. So even if you do see flows going this way, the solar wind did not reverse, okay? Solar wind is out here, way out here. And I've seen people use this. Oh, what happened? Oh, that's right, I've seen people use this so many times the wrong way that it just gets irritating. Solar wind is out here, guys. Out here's the bow shock, here's the Earth's magnetic system. Out here is the solar wind, folks. Actually, that probably isn't even the solar wind. That's probably still the lobes, yeah. The solar wind would be out here, okay? You're not going to see solar wind moving this way out here. You'll see solar wind moving out this way, which is the blue. You see this wishbone light up, right? You see the wishbone light up. See it? Because what you're getting is a slingshot being pulled back, it being let go, and it's slinging all this stuff forward in the tail of the Earth's magnetic system, seeing all this stuff forward, and as it gets closer, the magnetic field lines diverge and they become more what we call dipolar, and therefore they go and they link up, because the foot points of the magnetic field lines link up to the north and the south poles when they're this far out. And so, because the particles are jailed by the field, they have to go into the north and the south poles. I believe this is the meridional. Yeah, so you see north, south. So this is a cut through straight down the middle. Okay, the equator of the Earth is here. Okay, this one is looking down at the North Pole from the top, and you're seeing drift. You're seeing particles drifting in and around the Earth's magnetic system. Here they're being deposited in to the Earth's into the atmosphere, into the ionosphere from the north and the south. These are bursty bulk flows, okay? This is what causes aurora. It has to do this, right? Down the tail on the other side of the slingshot, there's a slingshot that shoots stuff down the tail too, okay? Because there's something called an X-line. If you want to go to my M series of courses, you can see this process in action. So this is normal. There's nothing abnormal about these flows. Nothing abnormal about these flows. On top of this, this is a model. This isn't data. we don't have and I've seen this happen so many times, where people are thinking that this is actually real data. We don't have an armada of spacecraft. We don't have like Starlink out here in the middle of, all of these populating this entire region. I'm sure scientists would love to have that if we could ever get there, but it's incredibly expensive, right? Space is very big, it's very vast. So to try to have all these areas populated with spacecraft, it's not doable, okay, to put it simply. And so these are models that are running, okay, and they're taking solar wind inputs from our upstream monitor out here, not this one. This one is in the near Earth system, but out even about 400 Earth radii out front. And that is the input into these models that then create a near Earth system for us to look at. Okay, but these models are extremely useful because they can give us insights as to what we're seeing when we're looking at, let's say, the GOES magnetometer. Right, and I talked about this, and I think I even talked about substorms, where you can see substorms light up, right? And this is great for aurora photographers, but that's an advanced topic, okay? And I won't talk about it too much right now. We'll go and talk about it more, how you use magnetometers in concert with ground magnetometers. So magnetometer at the geosynchronous orbit in concert with magnetometers on the ground, and and also looking at other indices like AE, the suite of AE indices. So AE, AU, AL, AO, if you want to use AO. We'll talk about the detail about how those can work together, and where they work best, right? For instance, this set of spacecraft work really, really well if you're in the Western Hemisphere, especially in the north, but not so well if you're in Europe, right? It can. Not so well if you're in Australia, but it can if you know what you're looking at and if you know how to read it. So we'll discuss more of that when we dive into the advanced topics, right? But as a kind of a check, what you can see when you see this kind of stuff, right? These little wiggles and bumps, especially if you're near midnight, which we talked about before. And I'll show you that. This is when we had one spacecraft. Here's with two spacecraft, right? You're supposed to see this stuff go up, down, up, down, up, down, right? But here's a really nice substorm, load and release. So you're loading the slingshot and you're letting it go. These substorms can cause brightening in aurora that you may or may not be captured in other indices. It all depends upon where you are and how often these substorms occur. But you can see quite a few of them, right? Boom, boom. And again, they're more important, or more, I don't want to say relevant, but more accurate when it comes to auroral brightening when you're reading them near midnight. They're local midnight, okay? If you're not lined up with these spacecraft, the spacecraft are basically lined up with the east coast of the United States and the west coast of the United States. So you have goes east, goes west. That's what they're talking about. It's very United States centric, sadly, or Western Hemisphere, Northern Hemisphere centric, right? North America centric, I guess I should say. So I wish we had more spacecraft that had all the way around the globe. We have the LANO spacecraft, but it's hard to get their magnetic field data. But if we had more magnetic field data in GEO, I know Japan, JAXA has some, hard to get real-time data for it. If we could do a much better job forecasting substorms for everybody, right, all around the globe. Hopefully that's coming soon. And I talked also about what happens when you get a really strong solar storm impact, big geomagnetic storm impact. Oftentimes you'll see, instead of this nice smooth up, down with just some wiggles in there or some substorms letting up, this is not a substorm, okay? When you get something like this, you're getting the magnetosphere is being pushed into the orbit of geosynchronous. And so what's happening is that you're actually popping out, typically you're popping out into the magnetosheath. Okay, and I think I showed that here, right? Where this spacecraft is kind of just sitting there, and sometimes with these during the May 10th storm, you'll see the if it comes back, okay, you can see the solar wind right here. You can see that bow shock push all the way down in here. And when you do that, you can get your spacecraft sitting in the disorganized area, look at it like right in here, in the disorganized region of the Earth's magnetic system. And when it gets compressed like that, that's what happens, is that basically all hell breaks loose. Okay, and so you'll see like this, and then things will get quiet and it'll go back to being smooth. And if you're wondering why does it go up and then down and then up and then down, well, as the spacecraft goes around Earth, you go into the compressed region, right? The day side is the compressed region of the compressed lobe of the Earth's magnetic system, so the magnetic field goes up. And as it moves to dusk into the tail, well, that's the less compressed region, and so the field goes down. So it's smoothly in a diurnal variation every 24 hours. It goes from weak to stronger, stronger, strong, to weaker, weaker, weak. Get it? To stronger, stronger, strong, to weaker, weaker, weak. Get me? And that's the up, down, up, down, up, down. Watch it. Very, very, not uniform necessarily, right? You can definitely tell we had more of an impact here, right? Because the stronger went way strong, and then you had some substorms, right? But you're looking at the strength of the field in the geosynchronous environment. Two different spacecraft slightly offset from one another. That's why the traces don't line up. Okay. And then when you see arc jets, well, that's just maneuvers and things that letting you know that those are processes that are occurring on the spacecraft itself. Those aren't space weather or near-Earth environment changes. Those are spacecraft changes, okay, that cause, because magnetometers see everything, absolutely everything. Okay, again, still a review. And then the last thing I talked about just slightly are proton and particle radiation storms. And I probably won't have time to talk about them again today. I want to go over some other products with you, mainly things like NERAs and Avidos. Those will help couch some of the stuff that you see when you're looking at GOES radiation storm. You know, these are solar energetic particle events data here in Geosync. I also might show you some in the interplanetary medium too when we talk about advanced data products, because we could look at the ACE-SIS, for instance, instrument to get a better feel for what these look like out out even ahead of Geosync. Do they look a lot different? Yeah, not totally. You will see some differences. Do they end up hitting ACE faster than GOES? Yes, but not by much, because these are relativistic. So you have to get to really pretty short time scales to see the difference. But it's still useful, especially if for whatever reason GOES isn't here, right, or the instrument is having outages. It's always nice to have backups for stuff like that. But we'll talk more about how energetic particles enter the Earth's magnetic system and when, what they're useful for. Okay, but I may not be able to get to them today. But at any rate, in D1 I did talk about them again. This is on the GOES spacecraft. It's at Geosynchronous. We have multiple energies here, and these guys just now recently put on 500 MeV particles, which you'll probably basically never see go up. If it does, it'll be a surprise. But the low energy stuff, that's the red line, that's the 10 MeV and above, because this is what we call integrated flux. When you see this will always be the first line that goes up, and it always will be the one that goes up the highest. Okay. We also have the blue and the green line. I believe the blue line is for what, 50 or 30? 50 MeV and above. The green line is for 100 MeV and above. The green line and the red line are how we determine whether or not we have an S-level radiation storm. It's either or. The S level has to pop over what we call 10 PFU, this is 10 to the 1, 10 to the 0, 10 to the minus 1. I'm sorry that these numbers look so terrible, but that's what it is because it's a logarithmic scale. So once the red line reaches 10 particles per, particle flux units, which is that's what this label is, protons per square centimeter per second per steradian. That's a PFU, okay? So, then the numbers here have to do with the geometric factor. So, I'm not going to go into the details. We can go into the details when we talk about advanced stuff. Just know that these are what we call particle flux units. And once the red line crosses this at 10 PFU, or the green line crosses 10 to the 0, meaning 1 PFU. 10 to the 0th power is 1. Okay, so the green line passes this one, this little bar down here, or the red one passes this bar up here. Either way, you're in an S1 level radiation storm. Why? Why does the green have to only pass smaller level? Well, because it's much more energetic. And with these more energetic particles, it doesn't take as much to cause big showers, to pass through lots of shielding. It's much more biologically effective in humans, especially at aviation levels. Okay, so that's why we have that second warning. And most of the time we have what we call soft spectrums, which are the low energy only, but sometimes we have really hard spectrums where you see a rise in the or in the higher energy particles as well. And those are the ones that we really worry about. In fact, those are the ones that the ISS really worries about, right? Far more than these. Oftentimes they almost don't care unless they're at S2 or S3 levels way up here. But if they have high energy component, you better believe the surgeon is paying attention, right? The SHRAG is paying attention. So that's why we have that. And that's also dangerous for avionics as well. Okay, and that is our review. So what I'll do is I'll pause for just a second and I'll put up the chat here and we'll just chat for a sec and see if there's any questions that you guys have about the review, about what we've gone over thus far. You guys are talking about Elon, huh? Uh-oh. What do you do now? Hi guys, how's it going? I actually like this course today. We've got 190 people concurrently watching at the moment. It's kind of nice and quiet. You guys are, I needed a quiet day. This is kind of nice. Hopefully most of you are Patreon folks, because it's always nice when we kind of feel like it's a family getting together, chatting about stuff. Hello from Saskatoon. Hi Jeff, good to see you. Glad you're here. The TS 440s went crazy, Rod. What are the TS 440s? None were really asked. That's great. Okay, Jerry, thank you. Glad you guys are enjoying it. Glad you guys are, you know, understanding at least, right? No problems there. Okay, good. Thanks for the information. I'm an amateur radio operator for Trinidad and Tobago and find this helpful to understand radio propagation. Awesome. You're going to love what we're going to go into next. Because we're just going to start really getting into the ionosphere with the ionospheric stuff. That's a perfect segue. Oh, Kenwood. Okay, got it. Yeah, that's a perfect segue because actually as I talk about solar cycle progression, we're going to talk about some of the data products that have been used by amateur radio operators, I guess historically, maybe because way back when that was all we had, but we have a lot other better things to use now, and I'm hoping that more and more amateur radio operators will begin using some of these other tools that will be much more useful to them. So we're going to clarify a few things here, especially with the solar cycle progression, because we're going to talk about F10.7 flux, and we're going to talk about, let's see, F10.7 and sunspot number and X-ray flux and how they all kind of go together, okay? No, you didn't miss anything, Metal Halo. No, you're fine. Oh, that's cool, Spirit. Good to know. Good to know. You'll definitely have a great family. We're a really tight-knit family there on Patreon, so, and you get a lot more access to me. I don't want to know what Elon did. Okay, la 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 la. I'll do that. You invited your Eras team to watch. Thank you, Chris. I appreciate that. That's really awesome. Okay, you just found me today. You're very welcome. Jersey girl, that's awesome. Hopefully, just know that the information that I've already gone through, I went through in a previous course, so I kind of glossed through it this time. I go into things much more in depth, as you'll see here shortly. Okay, awesome, guys. Okay, so I'll take the chat back off. Thank you, Steffi, for letting me know. And we will jump into the next set. Okay. I'm going to be focusing much more on aurora and amateur radio. To start with, let's talk about sunspot number progression for a minute, right? Everybody's interested in the sunspot number, and people say, oh, there is no daily sunspot number. Sunspot numbers only come out monthly or smoothed or yearly. Well, that's not true. If you go to SILSO, for example, they actually put out daily sunspot numbers, and they are a mess all over the place. The reason why you see typically a monthly number or even a monthly smooth number where they smooth over, I don't know, maybe 2 or 3 months to get a softer line is because even averaging sunspot numbers over a month, it's still ratty. Look at the blue line. Okay? The reason for that is because the way the sun works, remember the sun is constantly rotating. Every 27 days we get a new, it starts over. And so over the course of a single rotation, there may be very active clusters on certain parts of the disk, both in the northern hemisphere and the southern hemisphere. And so that changes dramatically. This is oftentimes why you'll see if you ever watch some of the smooth sunspot numbers, you'll actually see activity go up and down, even over a longer baseline. Okay? That's why you get these pulses. You can even see them here. See this pulse? And then it goes back down, and then this pulse again, and then it goes back down, and then pretty soon we'll see another pulse again, and it'll go back down. And so you really do get these very periodic, intensifications. And that changes dramatically, right? So sunspot number, depending upon whether you're looking at it daily, monthly, smoothed, or even yearly numbers, really makes a huge difference in terms of what you can take away when it comes to solar activity. Now, way back when, sunspot numbers was all people used, right? And so it's still very much indicated or shown in a lot of space weather data products. How useful is it for space weather? Not very. It's just not very. What is it useful for? Solar min, solar max type stuff. Ascending phase, descending phase, right? Can you get ideas of activity, or at least the potential for activity? Sure, right? Because you can see when things go up and down. But really over a daily time scale, the daily numbers are just kind of messy. And just because you have a lot of sunspot numbers on the Earth-facing disk doesn't necessarily mean they're active, right? So you can have a lot of sunspot numbers and have absolutely no big flare risk. And that also means that you may or may not have a lot of solar flux. Okay, so some people use sunspot number and solar flux interchangeably, and you really shouldn't, because you can have lots of sunspots and have them all be pretty dim, and so you're not really emitting. Well, I should be very careful when I say that. You can have lots of sunspots on the disk and have the disk still be pretty dim. But if you do want to look at daily number, for example, go to SILSO, okay, and you can see the website right here. Right, that's probably the best place to go. And you can get both the plots as I'm showing here or the actual the data. If you go to the Space Weather Prediction Center by contrast or by comparison, either way, you will see the data. You'll see the sunspot numbers going up and down, but it's only monthly. Okay, so that's the best resolution you'll get, right? And so you can see that peak here and that peak here, just like we saw the peak here and the peak here. Okay, but you don't get the daily fluctuations. All right, just letting you know. And then, of course, another really great one to look at, and please forgive me if I'm wrong, I did this by memory. F10.7, that's 2800, isn't it? Megahertz? Am I wrong? I don't remember. Forgive me if it's wrong. I realized that this morning. I said, oh, I needed to check that. I didn't check that. I just pulled it out of my old memory bank, and my memories have failed me recently. So here's the location for the Lizard Penticton radio flux. This is, whoops, I'm phasing in and out here, guys. Okay. the Penticton radio flux, this is a really great place to get it. What's nice about getting it from Lizard is that these guys at Penticton, they take 3 different data plot points a day. And so you have to actually, the link, that if you go here, this link will take you to an opening page, and you'll have to look at it and say, okay, make plots, or go to the actual data, and then it will plot the data for you. And then just very similar to the SWPC sliders, you can slide in or zoom in and just get a few days. So like here, for example, is, if I can read this, my goodness, hard to read, October 23rd through November 8th. October 23rd here, all the way through November 8th. And you can see 3 points a day. And the reason why they do that is so they can ensure that they're not getting data that's too close to the horizon. They want to make sure that it's close to zenith. And they take one during zenith, their local zenith, but then they take some, and they want, so they can get a little bit of change. Sometimes they can get a little bit of a rise or fall. This is the observed flux. This is the adjusted flux. The adjusted flux is adjusted according to a spectrum that has been in existence for a very long time. Whether or not that spectrum is correct, they still kind of say, well, if we had to do it again, we would change how we do the adjusted flux. We've learned a lot more about solar flux, but because historically it's been done this way, they keep doing it. So that's why they have the observed and the adjusted flux. And this is what people have used, right? F10.7 flux levels to get an idea of what radio propagation on Earth's day side should be. If you're sitting down at the, low 70s, your radio propagation on the day side isn't going to look very good. Once you get over about 100, then your radio propagation is looking pretty good. If you're getting up to the 150s or 200s or even higher, right? We were almost in the 300s not that long ago. Then radio propagation should be fantastic. I mean, you should be able to go all the way around, all on the day side, even pop it into the night side using even day side radio bands to communicate even on the night side a little bit. Except F10.7 tells you the potential for good radio propagation on the day side. It doesn't tell you anything about the noise, right? Because oftentimes when radio propagation, or when F10.7 flux goes up, well, that means you typically have a lot of really bad actors on the sun, especially if it goes up quickly. You have a lot of bad actors on the sun that are making a lot of radio noise, okay? So one thing that you want to use along with that, oh poop, I'm skipping ahead of myself. Okay, I'll do it. One thing that you want to use along with that is X-ray flux, okay? But we'll talk about that in a minute. First, I forgot to tell you, Penticton flux at Lizard is great because, like I said, you can get to see 3 points a day. You can get an idea of if things are like something like this, probably not good. This isn't probably real. What's happening here is that they're measuring during a big solar flare. Okay, so if one of them is a real strong outlier, if you can see the 3 points here, boop, boop, boop. One of them is big, strong outlier, then, that's because it's probably being contaminated, so to speak, by a space weather event. But for the most part, sorry about the sunlight is peeking through. For the most part, you can get a nice feel for what the solar flux is doing, radio flux is doing over the course of a day. But when you look at the same thing on the Space Weather Prediction Center site, once again, you get monthly values here. The only place to get the actual radio flux on the Space Weather Prediction Center live daily is to look at this number here. Okay, and you can get records of that for sure if you look at some other areas on this site. But it's really one number a day. That's it. They take it at noon, and you're done. Okay. So that's the number today, which is really good, right? You'd think. Now let me go back here. So I prefer the Lizard because of that you can get a better feel for what the flux is actually doing. But on top of that, I never look at the Penticton flux alone, right? What I look at is I'll look at the F10.7 and then I also look at the X-ray radio flux. And the reason for that is because the X-ray flux, and you oftentimes see in my forecasts, when I talk about flux, I won't show Penticton. I won't show the F10.7. I just show X-ray flux. And the reason for that is because I care more about the noise. I can take that single number that we get during the day, and we know that radio flux is going to be, or that the radio flux is going to be good when we have X-ray flux high. The problem is, where does that noise floor lie? Okay, and as I talked about the X-ray flux last time and then this time, I said our noise floor typically right now during solar max is between the C floor and the M floor, right? And that's exactly where we are, right here. So if you were to take out all these little bumps and wiggles and just smooth it out, you see this kind of lumpy, kind of like, line that's hovering in anywhere between the C and the M class flares right now. That's noisy, right? Especially when we get up to the M class level as a noise floor, where all the flares are popping above that. Look at this. This is where our noise floor was. This is like just a hair below the M class level. This is R1 radio blackout level. Okay? That's noisy. If the sun is just making that much noise, that much cacophony, just without even flaring, you know the dayside bands are noisy, right? So oftentimes what I'll do when you combine, so this is beginning to show the power of combining different products together. You can see just from the X-ray flux where the noise floor begins to rise. You know it's going to be noisy here, okay? You can also see where the noise floor begins to fall. Notice it continues to fall. And if I were to go to the live product or live stuff, like right now, if I recall, take a look at the 7-day, make it big. See it rising, 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 right to here, falling, 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 and then it kind of evens out. Now we're just kind of like at a level, at about a C, I don't know, 3 level maybe. Okay? But you could see this. You can really see this. So sometimes the best thing to do is not to pay attention to where the flare peaks are. Look where the bottom is. Okay? And watch where after a solar flare, does the bottom continue to rise? Were you higher after the flare than you were before? Uh-oh. If you are, that means another flare is coming. But if you flare and then the bottom, the noise floor, where it settles down to, ends up being lower than you were before, well, maybe it's calmed things down again. And then you'll watch that noise floor rise again. You're like, uh-oh, here we go. So you literally can watch in the X-ray flux and get a feel for where you're, not just where the noise floor is, but also the potential for more flaring. Okay. And if you combine that with Penticton, for example, so this was a noise floor rising about midday on the 5th, and then falling about midday on the 6th. Let's take a look at the Penticton flux. Was it rising? No. And was it falling there? No. So what's that telling you is that there's a good chance, now granted we see it down here in the adjusted flux, so do I know this well enough to say, well, maybe it was rising and falling. What I will say is that it looks like it might have been delayed, but I'd have to kind of know, what I'd probably do is go to SWPC to make sure, to see where their adjusted flux was for that day, right? To see whether or not they're actually taking events during a solar flare or not, right? To get to understand what's going on here, because it's so different from this. Usually these two aren't that different. But in this case, if this is the way we're looking at solar flux, right? If we're seeing solar flux kind of being not following that rise and fall, then I would say that compared to the noise level here, this would be a much higher noise level because you're not seeing the solar flux rise, right? It's just kind of staying level during this period. So you're getting a noisier set of bands over the course of this day than you were afterwards. So sure enough, when you watch that floor rising and falling, I bet people had, on average, on the dayside bands, a bit more noise that they had to deal with, especially since we didn't see the F10.7 go up either. So they can be powerful tools if you use them together, especially for amateur radio. Used apart, yeah, they can tell you certain things, but used together, they can give you more insight. Okay, and that's one of the cool things about the basics. And these data sets are really robust. I've never yet gone to either of these sites and had them down. The only time SWPC ever goes down is when they give you a real maintenance thing, right? Every now and again, I mean once every 3 or 5 years, there'll be some hiccup where something goes extremely awry. But they are working on it right there. It's not like, oh, well, it happened on a weekend. Nobody works on the weekends. And you got to wait till Monday for people to come in and fix it. No, no, no. They're fixing it right then and there. So they're up as soon as absolutely possible. So these are really, basic data products. But when you use them in tandem and combine them, they can be extremely powerful. Okay, so that was, what did I call it? This was all mainly about progression, solar cycle progression, how to look at these data products, how to use them, how not to conflate solar sunspot number with your F10.7 with your X-ray flux, but rather how to use them in such a fashion that they enhance your understanding of your conditions, okay? And that's mainly, again, on the day side. All right, here's another one. Here's another really good data product to use, DRAP, okay? And I don't think I talked about it last time. Or maybe I did, and I don't think I talked about it last time. I might have shown it to you just a little bit, but DRAP is an amazing model. It's not data, okay? It's an amazing model. It's a very simple model, but what it basically shows you is the D layer of the ionosphere, right? Now, for those of you who are amateur radio operators, you guys know, right, you go from D to E to F1, F2 on Earth's day side. And of course, on the night side, the D layer disappears. The E layer may be sporadic-y during certain times of the year or during certain weather patterns, right? And then the F layers combine into a single layer. And the D layer is super important because it's extremely dense. The reason why it disappears on the night side is because there's particles that are banging into each other all the time, and all of that free electrons floating around that create the layer during the day side, because the atmosphere is being bombarded by photons from the sun, which then cause photodissociation, cause the molecules in the atmosphere to photoionize, and now you have free electrons running around with ions, right? Helps create the ionosphere. But on the night side, when you're at these really low altitudes, there's so many particles banging into one another that they're able to recapture those electrons very easily. And so that you get this recombination very quick. And so on the night side, the D layer goes away. But the thing is, when you get a solar flare, because there are so many particles in the D layer, you can photoionize that layer so much, or that altitude, so much that you get too much charge, get too many free electrons, and you completely make that layer opaque to radio propagation, to skywave, okay? And that's what you get, and that's what this model is basically talking about. There's two different things it's talking about. One are solar flare impacts, and that's what you see in this big circle, okay? This big circle is showing the day side, okay? If you can imagine, there's a night side terminator here, right? So here's the day side of Earth, the night side is in black, okay? And this thing rotates over the course of the day. You'll see this thing move. The map stays still, this thing moves. Okay? So what you're seeing here is the impact of a big solar flare. And what's neat is that it's showing you the highest frequency affected. Okay? So you're not seeing in this sense how much absorption. You're seeing 1 dB of absorption. Right, so how your signal will drop by 1 decibel. You do a sky wave, you transmit with this much power, and what you get back is 1 dB down, okay? Because you're getting absorption by the D layer. And it's not just showing, so I'm gonna be careful when I say this, I wanna make sure it's clear. We're not here in this plot, they're not showing how much absorption has occurred in a single frequency. They're showing you what frequency, up to what frequency is being impacted, okay? And by being impacted, that just means 1 dB down. So it may not be impacted to the point where you can't hear anything. It's a weaker signal that you're getting, or you're transmitting that the person on the other end is receiving. But it is telling you what frequency it goes up to. Okay, so if you're seeing red, every frequency in the HF band, right? Because you're 3 to 30. Every frequency and above, even in the VHF range, you're getting impacts. Again, it may not be so much as to completely wipe out these higher frequencies, because they may only be 1 dB down, but they are being impacted to some degree. Okay, and so if this is showing you, at least with the solar flares, it's showing you where that's happening. Okay, and what signals are being most impacted, right? So in this area, this isn't the most intensity, the strongest of the solar flare impacts. It's telling you that it's the highest frequencies are being impacted to some degree. To be totally honest, where the frequencies seem to be impacted the most, like the most intense, are where the colors change the fastest. The gradient causes so much more impacts in terms of causing signal scintillation, causing fades, signal fades, and all sorts of weird comb filtering stuff to happen. There's actually a lot more stuff going on in here, believe it or not, than in here. But in here is where you're getting the highest frequencies impacted by at least 1 decibel. Okay? Now, what does that mean in terms of how do I know how many dB down my signal is being impacted? Aha! That's when we turn to this plot. Okay? These are not measuring the same thing. The map is showing where and to what highest frequency is being impacted. This is now showing you how much. What's the attenuation? Okay? And so you're reading frequency, okay, 5 megahertz all the way up to 35 megahertz, so just above the cutoff for HF. And now you're seeing the attenuation in dB. Down here on this plot, 0 to what, 30, 40? What is it saying? 35, it's showing 35. Yeah, they shouldn't have shown 35, because man, it gets confusing, doesn't it? Because now you're thinking that's the frequency. No, wait, that's not the frequency. No, this is decibels down. Okay, so how much attenuation? How much of your signal has been absorbed? And it's always going to be that your lower frequencies get impacted more, just more intense. So you're losing more than 30, it's pegged, as you can see. You're losing more than 30 decibels or 35 decibels if you're working 3 megahertz, 5 megahertz, all the way up, in this case, up to about 10 megahertz. Now you're seeing, I'm only seeing, well, in this case, 30. Okay, 30 decibels down. But as you get up to 15, let's say 17, right? Now you're looking at, what, 10, 15 dB down? Not so bad. Right, so you still can probably manage. If you go to even higher frequencies, well, now it's only a few decibels, maybe 5 dB down, maybe 4 dB down, right? So it's still being impacted, but you're probably able to get through that, as long as you're not working, 1 watt, right? Crank up the power a little, and maybe you can get through, right? Because it won't absorb all your, it won't attenuate your signal all the way. Okay, so that's what this is telling you. And again, it's a model. This is not hard science, right? It's not hard, I shouldn't say that. It's not empirical from the perspective of actual anecdotal reports coming in and showing you this. This is a model. But at least it gives you an idea. This is how much you expect of your signal to be attenuated depending upon the frequency you're working. This is where you can expect attenuation of only 1 dB, okay, at least 1 dB, with the frequency labeled by the color. Okay? And obviously, if you're in the black, nothing's impacting you. But if you're on the black, you're on the day side. You're on the night side of Earth. Sorry, you're on the night side, right? Because if you can't see the sun, you can't hear it scream, and it can't impact you. Okay. So that leads me to the next thing. What's going on at the poles then? What's going on in the North Pole and in the South Pole? Well, the neat thing about DRAP is that it doesn't just indicate what's going on with solar flares. It also tracks polar cap absorption events. Polar cap absorption events are when you get solar energetic particles, so there's radiation storms, into the polar caps. Okay, so anytime you have an SEP, or also known as a radiation storm, you're going to have polar cap absorption events. And that's what this is labeling. Okay, so honestly, this is actually combining the two, right? You're getting this much attenuation, not just from the solar flare, but also from the radiation storm that's ongoing. And again, right, it's red because it's saying that 35 megahertz, and likely higher, are being impacted by at least 1 dB. And that's because, honestly, radiation storms, you're getting cosmic ray showers, they don't care what frequency you're on, you're just in trouble. Radiation storms can scintillate signals, even GPS signals that are at, 1.5 gigabytes, or gigahertz, 1.5 gigahertz essentially, right? L1, L2 is at 1.2 and then 1.4 or 3 or something like that. 1.5 gigs, Polar cap absorption events may even impact Starlink. I don't know. Sitting at 12 gigs, right? 12 to 15 gigs or something, wherever it's, I think it's got a range of frequencies it's using now. Last I heard, Elon is trying to get Starlink to work at 70 gigahertz. Whew. I don't know about you, but I don't know if I want to be in a 70 gigahertz beam. Does anybody have a clue of what the health impact of a 70 gigahertz beam is? I just don't know. 5G is bad enough, so I'm not sure about that. But anyway, so the neat thing about DRAP, the DRAP model, is that it gives you a very quick look view of both solar flares, the impact of solar flares, and the impact of radiation storms. Two different, fundamentally different, but very impactful space weather phenomena, all in one cute little package, okay? And it's in real time. So if we were to go to DRAP right now, which I go to Products and Data, as you can see, and then you go to Models, and I'll zoom in, Models, and we go to, there it is, D, Region, Absorption, Predictions, DRAP. And hopefully it will load. Oh, good. And so this is what it looks like right now. Boring. No radiation storm. Okay. But you can tell, see how it's lit a bit more down here compared to up here? You know why? Seasons, right? We're getting into the southern hemisphere spring. So the sun is lighting up the polar regions, the southern polar regions, more than the northern polar regions, right? We're getting close to the northern hemisphere winter. And so you'll see that change, right? As if you had an NLMA to draw across this so you could see where the sun is, you'd know the sun is kind of, its center, as you can even see here, here's the center where you see these tiny little pops. This is small little solar flares occurring. The center of the sun, what was it, resets? The center of the sun is it's hitting Earth. Notice it's just below the equator, right? We're south of the equator, so it tells you, that also tells you where we are relative to, where we are in the seasons. But if we had a radiation storm, both poles would be lighting up. The southern pole more than the northern pole, likely, just because you have the additional stuff from the photoionization of the D layer. Remember, this is just the D layer of the upper atmosphere. And now, and of course, there's the day side, right? And the night side, nothing's going on. So you can see that terminator, right? The gray line, right? And a lot of ham clocks have this. Now, what's neat about this is that you can actually go to the tabs at the Space Weather Prediction Center and look at the different frequencies. So you can isolate. Right, and I think, do they have these as movies? I don't think they have these as movies. But they have a now time, which sadly is kind of boring right now. See a little bit of pink right here. And then they show you global views. If you want the polar views, the North Pole looking down, the South Pole looking down, you can see again very little glow in the North Polar regions, if this is the North Pole, because the sun is, you know, on the other side. Southern polar region, you get a lot more glow because the sun is, it's southern hemisphere spring, almost summer, actually. And you can see your attenuation will be limited to 5 megahertz and above. Well, I don't know. They actually, I guess they show the attenuation for everything. They still show the same attenuation. It's just the map that changes. Okay. So, right, and so as you go up, the higher frequencies, let me go to like 30 megahertz, right? These are going to be black most of the time, except unless you have a really big solar flare, right? Because you're looking at the attenuation and the absorption at that frequency. And so these little teeny tiny pops, you're not seeing anything, right? So that's why I do global, because global shows everything, shows all the frequencies. And so you can get a better dynamic range, right? And if you wanted to look at the global, I mean does that go up to 10? Oh no, I guess it does. 10 dB absorption. I don't like that as much. Again, you're limiting. You can see it in the polar, and again, I don't think they have movies for these. No. Oh yeah, they do. They are movies. So you can watch it. But again, this is at 10 dB absorption. It'll be a lot more boring right now. But you can get polar views. And I think at NASA you can get even more, you can customize it even more to your needs. But for me, you know, I want it to be the most sensitive, so to speak. And that's going to be this version. And they don't have polar for that. Okay. Now, let's pause this for a sec and go back to, right, so this is when it looks a lot prettier, which is bad news for, do I have a movie? Yeah. This is bad news for amateur radio and just radio frequencies in general, right? Even VHF. So if you're an aviator, DRAP is a very good thing to look at because it gives you not just a map. This is, for instance, the DRAP during the May 10th set of events. So you see lots of big solar flares almost all the time. This is because our noise floor was so high, right? And pretty soon you'll see a radiation storm. There's some big X flares occurring. Well, those might not have been X. If they were impulsive. But we had lots of flares going on, as you can see, northern hemisphere, more northern hemisphere summer compared to the southern hemisphere, much more quiet. There we go. There's a nice big X flare. Might even get a radiation storm from this, I'm not sure. I forget how the timeline went. We'll see if there's a radiation storm that pops up. You'll be able to see it. Oftentimes it'll flash on and off at first because the DRAP model has these hard thresholds. I don't know if we're going to see it. Didn't we have a radiation storm during the Gannon event? This is still the 9th. If you can see it running here. But see, sometimes you'll see X flare, no data. It'll let you know when there's no data. It'll tell you, sometimes it'll give you an estimate of how much longer it's going to last. If it's a really big gradual event, it will give you that indicator. No, we didn't have a radiation storm, at least not through the 9th. Oh, bummer. Oh, I thought I had one that had a radiation storm pop in. Oh well. Anyway, it should give you that, you know, you can see this stuff moving, getting worse or better. But what's nice is that, especially if you're an aviator, it's useful because when you're looking at the sun, when you're up at high latitudes, the sun oftentimes is much lower to the horizon, even as you set, or if you're above the Arctic Circle, for example, and during the summer, the sun is like almost always there. I mean, it goes up to the zenith and then goes back down to the horizon. It stays at the horizon. And that's line of sight for you to communicate through VHF. Noisy. That's the last place you want the sun to be, is on the horizon, near the line of sight of your radio communications. Either you're firing into the sun or the sun's behind you and you're firing away from the sun, but the sun is in parallel. It's firing its signals, you know, in the same line of sight as you are. And so it can be very useful, even for aviators, when the sun is active, to pay attention to DRAP, because it gives you an idea of how sunlit you are, you know. and when you expect to have noise on your bands. Okay, let me see where I am real fast. All right, I'm going to do a couple more slides and then we'll take a short break while I ask questions about this data product. All right, so what I'm getting into now is still the same kind of concept, but we're going to put this together with another data product. And to go there, to get this particular data product, you go to G7IZU. This is actually, you can actually go to g7izu.co.uk. Or you can use this one too. Either of these work. Because this website run by Andy Smith, he's an amazing amazing person who's also an amateur radio operator, and he creates movies. He runs the program that's done by G7RAU. Oftentimes you see me use them in my forecasts showing amateur radio propagation over different frequencies on the day side, on the night side, all sorts of good stuff. And here's an example of radio propagation during the 10th of May. And so you can see, I don't have the scale up here, but I'll show it to you in the next set of slides. Here's what we call the subsolar point. This is where the noon is, where the sun is, as it's moving across. And all these different colors are different frequencies. And so you can actually see when they kind of duck, you can actually see when you have big solar flares occur. Sometimes there are data outages, but not very often. They're pretty short-lived. But it's very useful to see now for nowcasting of there was a big solar flare there. I don't know if you noticed it. It's very good for nowcasting of the dayside radio bands. You can see a terminator. It's kind of hard to see, I think, in this thing, but you can see kind of a thin gray line. It's showing like nautical twilight, I think, astronomical twilight, nautical twilight. I don't know. I forget what these two are. But you can see where the night side is clearly and where the day side is and where some of that gray line, where the different twilights are. And so, and he's got all this detail on his website. And so as you watch this thing go through with these different frequencies, and he does have a color code for the frequency right there. Whoop. Oh man, what happened? I'm trying to pause it when I get to it, when the flare occurs. Look at all the propagation you're seeing right now, and then suddenly it'll disappear. Right? Why aren't you cooperating? See if I can get out of the way again. Well, I'll stand on this side. There we go. See how it disappears? Right? So we had a bunch of propagation, and of course you can see the line still going this way. But look at where it disappears. Okay, here's where the sun is. And so you can actually see in real time kind of what the DRAP model said, this is what you would expect. Well, here's the actual data. Okay, so as you can imagine, looking at these movies, and there are movies, I actually help fund his site to make sure that these movies are available. Okay, because they are a really great way of just very quickly seeing what's being impacted at what frequency. And if you put the two together, okay, as I do here, as you've oftentimes seen in my forecasts, right? Because my Geochron data product, we're still working on it. I just don't have time to work on it, is really what's happened. It's only stalled, not because it's too hard to do, but because I'm pulled in too many different directions, right? But I will get it working. But until then, one great thing to do is actually look at these together. So again, putting things together, right, two basic data products together, you suddenly see, look at this. Look how amazing. You can see exactly where the flare occurs and what frequencies are being impacted, even as DRAP shows the on-off. So something that is, you know, two different data sets that are, or two different data products that are good, end up being great when you put them together. They can give you an idea not just of what you're expecting, maybe even how long you have to suffer, right? If it even tells you, sometimes it tells you. Yeah, this time it isn't. But it's also, you can also actually see what frequencies are really being lost and where, right? Because here's the night side, right? And you're seeing some short propagation, right? You're seeing short hops here, right, in these lower frequencies, or I mean higher frequencies rather. But, you know, so it's not a complete blackout, even though this is a R3 level radio blackout. But nonetheless, you're seeing, you know, you get a better feel for the model and the empirical or anecdotal data that's gotten straight from the databases. And then you also get to compare as the radio propagation either occurred prior, you know, before the flare or even after the flare. How long does it take for these frequencies to come back? And has yours come back yet? Right. So even though you see the flare still dying off, you can see that frequencies can come back very, very quickly, especially if it's an impulsive event. Or sometimes when we have big radio bursts and the event just glows and glows and glows, this will recover, but this won't. Okay, or vice versa. Okay, let's see. Now I might be at the stopping point. Yes. Okay, so I'll put this back up. Let me pause here and see if you guys have questions. Whoa, I see lots of conversation. Wahoo! You guys are writing paragraphs. Question, Doc. Okay, I see one. What kind of drag do our Earth satellites endure? Oh, and what part of a solar storm exacting Earth do they start to have issues? First of all, right, you're talking about LEO satellites, and it matters what altitude you're at. So that's the first thing that that's the first question you ask, of course, is that where's your satellite, right? And what part of a solar storm? The problem when you say what part of a solar storm is it depends upon the strength of the storm, right? It also depends upon how geoeffective that storm is. Because if you've got a lot of dynamic pressure and therefore you're inputting a lot of junk, and it's a dense storm, you're inputting a lot of material, even if you don't have a lot of what we call joule dissipation happening because you've got a lot of aurora going on, you can still have a pretty decent thermal, you know, impact to the ionosphere and start heating up that ionosphere, and causing and on top of that, if there's a radiation storm occurring along with it, once again now you've got cosmic rays that are cosmic ray showers, and those polar cap absorption events, those help heat the ionosphere as well. So it really depends. It's almost a case-by-case basis. Another example that I talked about, I think I did a whole briefing on this when it happened back in 2022, 2023, when did it happen? I think 2022, when Starlink fell out of the sky. And it was this really puny G1 relative to the KP index, right, what we saw. And yet I was laughing because I knew what the problem was. Everybody was like, well, why is this? Why would a silly little G1 take out 40 satellites? The issue was not just the fact that Elon was doing an orbit insertion at about 210 kilometers, which was way too low. We had been screaming about this for years, saying, don't do this. He needed to make them higher. But this particular storm also had a certain kind of preconditioning that set up a circulation pattern for more than 24 hours, a decently strong circulation pattern for more than 24 hours that was very different than the storm time pattern that is set up when you have a geoeffective event. And in this case, when you reverse, and I talked about this in detail, when you reverse the pattern of convection in the upper ionosphere, and this happens through the current systems, Hall and Pedersen currents that are occurring, and those are being created by literally how the solar wind is coupling with the Earth's magnetic field up front. You create these think of it like a witch's cauldron, and she's stirring, okay? So she's got 2 spoons and she's stirring a particular way up in the upper poles, and in the northern pole and then the southern pole. And she's stirring a particular way, and suddenly you have to reverse. Just like when you stir your coffee and suddenly you reverse your spoon. Boy, that creates a lot of craziness, right? Creates a lot of friction. And so in this case, what we had was a very strong northward magnetic field for more than 24 hours. And then suddenly it just took a nosedive and the field turned south really, really strong for like almost 20 nanotesla, if I recall. And then it recovered reasonably quickly. It wasn't like this huge thing. It didn't last all that long. But even the people on the ground, they were looking at this saying, I don't understand. We have this really strong magnetic field. We should have a very strong response. And yet we're only getting G1 levels, and the aurora looks really weird. The aurora looked very diffuse. It didn't have a lot of discrete arcs. We didn't have the normal substorming we would have. It was just very bizarre. And everybody said it was very surreal. And the reason why was because we had set up what's called a polar vortex. We had actually caused the neutral atmosphere to get churning in a particular way. And just because the magnetic field changed, right? And so now the ionosphere is being churned the other way because it sees electric and magnetic fields and it sees the switch. The neutrals are like, I don't see anything. Let's just keep going. They were like stampeding in a particular pattern. And now all the charged particles up there are stampeding the other way. So you're getting a lot of this, a lot of friction, right? And so that's what caused the heating of the thermosphere in a very dramatic way. Yet the geomagnetic indices, G1. Okay. So it's a very difficult thing to answer when it comes to these, to lighting up the thermosphere. Or not lighting it up, but heating it up. Because there's lots of different inputs, and preconditioning means so much. I mean, it can literally be the story or not. And sadly, a lot of the models that we have to this day, the operational models, don't have a very long set of preconditioning. They'll set up a preconditioning for maybe 3, maybe 6 hours if you're lucky. But you don't see preconditioning for 24 or more in all of our atmospheric models. You just don't see it yet. And part of that is well, I won't speculate as to why we don't precondition for longer. I will say that some of that is operational complexities. Let's put it that way. But some of that is really protocols that should be changed. But I do think that there's new testing that has to go because I won't get into the details. Some of it I can speculate on, but I don't want to say the wrong thing and make a big deal out of something that may not be a big deal. I don't do operational test beds, so I have my hunches as to why we don't do preconditioning for long periods of time. But I don't, I'm not gonna voice those here. Maybe behind the scenes in Patreon, I'll voice them, but I won't voice them here. But hopefully that answers the question. Is you can start storming, you can start having thermospheric effects right away. Now, here's the thing: they don't end right away, so it's not an on-off. With the thermosphere, it typically takes days. So will you start seeing in let's say a situation where it's not preconditioned, where you don't have any pre-existing condition going on, there will be a delay. Typically, could be anywhere between 12 to 2 days, 12 hours to 2 days. And then you will continue to build up problems for maybe a day or two after that, and then things will slowly settle down. But again, it is still case-by-case dependent. It also is orbit dependent, right? Where's your orbit? How high? Right? If you get above 600 kilometers, we almost don't care anymore. You can pretty much overcome, a lot of stuff. Now, if it were a Carrington-class event, well, yeah, we saw orbit issues. We saw huge scale, their density fluctuations clear up to 900 kilometers. I mean, we saw massive ones. This was, I'm thinking of the 1972 event in August. So could you affect spacecraft, satellites clear up at 900 kilometers or even 1,000 kilometers? Yeah, sure you could. But those are rare, right? Most of the time when we think of about 600 to 650, that's where things get easier, right? But if you're down in the 400s, God forbid, you're lower, you're in real trouble. Okay. Hopefully that answered that question. So if you guys have other questions, let's see. I will, you'll have to repeat them. Okay. How are we going to prepare for solar maximum in 2025? Well, first of all, we're already past the peak, so to speak, because solar maximum is both a phase and a peak. Okay. So those of you who think that solar maximum is yet to occur, we actually have already passed the peak. And we know that for several different reasons. But that being said, especially since this is an odd cycle, solar activity will continue to climb over the next few years. But the nice thing is in about a year and a half or so from now, things will become a lot more predictable because coronal holes will win the battle. Right now, we're kind of beginning to see, if you look on the sun right now, as a matter of fact, I can do this because this is important. If I go to the sun and I pick a wavelength, oh, I should do this. What might be, yeah, it's good enough. Here we go. Sorry if I'm making you dizzy. Boy, it's in a crazy, crazy sun right now, isn't it? So if I look at the sun right now in 193, for example, 193 angstroms, because that's a good wavelength for you to take a look at the features, multiple features, not just the bright regions, but also filaments and also coronal holes. Okay, this is oftentimes why we use 193 or 195 for a beacon style instrument. That's why stereo A has its 195 as beacon imagery, which means low res imagery but fast getting to you. The reason why we use this stuff is because we can see all the features, right? So what we're beginning to see with this crazy looking sun is a battleground now between sunspots, right, in here, and coronal holes. Okay, so we have fast wind, which creates storms. We have active regions, which creates coronal mass ejections. We have filaments that are also coronal mass ejections if they launch, right? We can have, so you can get coronal mass ejections from all sorts of places, right? These big solar storms can launch from anywhere. But you also have now fast solar wind to contend with, and the deflection and everything else that goes along with it, and the instability that comes with having these coronal holes kind of jostling for position and trying to move into the position they need to move into over the next couple of years. And so activity actually increases. Okay? And as coronal holes become even more trans-equatorial, meaning that they cross the equator, you're going to start seeing fingers that are crossing the equator. As you start seeing them become larger and more plentiful, as we move into the declining phase of the solar cycle, we will start getting these recurrent fast wind streams that will cause typically G1 to G2, sometimes G3 if you happen to have a little CME, a little solar storm launched in there with it. You will start seeing these storms every 27 days. And so activity actually increases. Okay. So just because we've passed the hump of peak sunspot number, peak solar maximum, doesn't mean activity is dying down. If anything, it's increasing because the battle is just beginning to heat up. And you'll start seeing the most interesting looking star. If that wasn't an interesting enough looking picture, you'll continue to see it. And just watch over the course of time. Watch these coronal holes get bigger and bigger and bigger. And that's when everybody's going to say, oh my gosh, the sun is falling apart. It's got this hole, it's cracking in half. Or they'll say, oh my gosh, our dynamo, it's dying. Look at the hole in the sun, it's dying. Oh, no, it's not dying. This is normal. Okay. So I see, good question, Ray. It's a great answer too. I hope she sees your question. What question am I missing? Greg Wall says, that made me wonder if they peak separately, does that mean that the peak intensity will be protracted over time, but perhaps not as strong as if they peaked together? You talking about the hemispheres? Yes. If you're talking about the solar hemispheres, that's what we call solar hemispheric asymmetry. And when the two hemispheres peak together, that's when we get the super strong sunspot or solar cycles, like cycle 19, like cycle 22, right? When they are not peaking together, that's when you get weaker cycles. And I talked about this during the course, the Breathing Heliosphere. So I think that's the H series. I talked very much about this. And Scott McIntosh and crew, who now are at Linker Space, they have a very good empirical model based on the asymmetry of the hemispheres, and have by far the best prediction model out there for solar cycle activity. Okay, I heard online that in 2025 a superstorm will wipe out all power in the internet, and it will take months or years to get the electricity back. How worried should we be? First of all, you can't ever predict when these storms are going to actually hit us. Second of all, we've already had, a super solar storm. That was the G5 in May. We almost had a G5 in October. We have these big events happen every solar cycle. And in actuality, probably the biggest one is going to happen in the declining phase. So probably not until 2026 or even 2027. And we will mitigate through. We have so much awareness now that we can help. We can dial down our power usage. I've even talked to people who do risk assessment for the Department of Energy, and they've talked about soliciting the public's help if there happens to be a very massive storm like a Carrington class event, to help free up, to dial down the true power so that you can free up more of the grid for reactive power, which it needs, because it needs power. It needs to be able to store more energy, because really what GICs, what the big geomagnetically induced currents cause, is it's green energy. It's free energy. But the grids aren't designed to take that energy in. And so we have different ways of decoupling the grid from the ground, because that's where the energy is coming from. And so we have ways of doing that in some areas, and that seems to be working. That's what happened with the G5. But we also can solicit help from regular folks, so we don't have to have things like rolling blackouts and stuff like that. None of this stuff has ever been tried before, right? But we have we've grown. The community has grown so large, and we've had so much more awareness in this cycle thus far, that I think it's worth talking about that. So when we do get big storms, just like I did with the G5, I talked about it. I said, hey guys, dial down your power usage. I said that both in May and in October. And luckily we've only had baby G5s, right? Little ones. We've not seen the really big ones. And so I still don't think we have a full test of our grid hardening, because there's been a lot of mitigating procedures that go into place during these big storms. So we haven't seen a huge test of it yet, but the tests that we have seen this year, we're doing better than we thought. So I have a lot more confidence to say I think we can ride these out pretty well. Yeah. Okay. That doesn't mean they don't need our help, but it does mean that you don't have to sit there and don't let this keep you up at night. Okay. Okay. Let's see. Question, doctor, is that giant sunspot in real time, and is it capable of speeding up any CME that happens within its site? You mean the sunspot, or you mean the coronal hole? Sunspots can't speed up CMEs. Sunspots launch CMEs, but they don't speed up any CMEs. If you're talking about the fast solar wind from the coronal holes, yes, they can speed them up, they can deflect them, they can do all sorts of things. In fact, they're a real nightmare when it comes to trying to understand whether a CME is going to hit us or not, especially if it's a glancing blow already, because the dang fast wind may blow it completely off the map and out off to the east or to the west or the north or the south of us. And so it makes it look like something that is going to hit Earth ends up missing us, or something we thought was going to miss us ends up hitting us because it deflects it into the Earth-Sun line. So yes, from that perspective, they can be blown in and out, but it's the fast solar wind that does it. Okay. My question was, does the moon affect our space weather in any way? Oh, interesting. First of all, this is just so you know, this is a lecture about the basics. So I'm not going to go too deep into that. But the moon does affect, the moon affects lots of stuff, right? The moon not only having tidal impacts, the moon affects our electric and magnetic fields around our Earth, And so there are diurnal variations that in magnetometers we have to take out. It's called the L variation, for instance, L for lunar. And we take those out. I think there's something like 10 to 15 nanotesla variations diurnally. So that it does affect from that perspective. Now, are you asking, does it affect a coronal mass ejection hitting Earth? Probably not. Earth doesn't even affect the coronal mass ejection. It's much bigger than the moon, right? So CMEs don't care. They're massive, right? They're taking their marching orders from the solar wind. And the solar wind is this big spider web all coming out from the sun, moving out radially from our star. And that's really dictating what the CMEs are going to do. Our moon is, just like Earth, is basically a needle through a haystack, right? It's just this pierce point. How much is going to actually affect a coronal mass ejection? Meh. Causing effects down at Earth? Oh, it's probably more in the noise. How would it affect anything? If it were magnetized, if our moon were magnetized, then it'd be a much different story. It would affect our aurora. We'd see it. It'd be like the Jovian system, and you have a moon like Io or Callisto or Ganymede, which have their own magnetic fields, right? They have their own magnetic systems, and these little magnetic systems are coupled into the big system, and wow, it's really cool. You get to see the footprints. Could you imagine if our moon were magnetized? Not only would we see aurora at the moon, so even if we didn't get to see aurora, like locally in our own sky, we could look up at the moon and see aurora in the north and south poles of the moon if it were a dipolar field. Wouldn't that be cool? Not just that, but then in our upper atmosphere, in the ionosphere, we'd actually see a foot point of that magnetized moon, its foot point up in our own ionosphere. And it would be like aurora that would just sit there in like this spot, like Jupiter's red spot, but it'd be an auroral spot, and it would just follow where the moon is in its orbit. And it might even be active even when space weather's quiet. So wouldn't that be neat? You'd have this little glow up in the upper atmosphere if we had a magnetized moon. So less impactful because it's not magnetized. But we absolutely see impacts at other planetary systems where their moons are magnetized, Jupiter and Saturn, for example. Yeah, so maybe I'll do a course on that someday. But kind of neat, huh? I almost wish we had a magnetized moon. It would be a lot. We sure make going to having the Artemis mission be a bit easier. I think we'd get a little bit more protection, even though these guys are going to the poles. I think we'd get at least a little bit more protection from things like radiation storms. I really worry about our Artemis folks going to the moon during solar maximum when we have a chance of getting big radiation storms. I don't know about you, but I don't want to be standing near a water wall or in a water coffin for 2 or 3 days. I mean, how do you do that without losing your mind? Because you're trying to protect yourself from a radiation storm. It just seems nuts to me, but that's all I'm going to say about there. Okay. Yes, Barb, I do. I drink out of a mason jar. Yes, I do. So do my moderators. They've got their own mason jars. A lot of my VIPs have their own mason jars. Okay. Hopefully that answered that question. Any other questions related to this? More related to this? Yeah, Jerry's like, stay on topic. Last question for me, Doc. How do I take your class? You mean my Millersville University class? Go to Millersville. Go to Millersville University. I think it's Miller. I even say it on my forecast. You can see the website. I think it's millersville.edu/SWEN, SWEN, for space weather environment. Environment, yeah, space weather. EN is meaning environment. And it's a science course, so you can apply there if you want to take it for like the actual certificate program and get an official certificate. Then you need to sign up as an official student. If you are, however, like a lifelong learner, or you want to take it as like an enrichment program, right, kind of like as an extension program, there are other ways to take it. You just don't take it for a grade. So you can take it for for a personal enrichment, personal credit. And then it's much, much cheaper. Otherwise, you're paying for the whole university, to be an official student, to get an official document from an accredited university saying you are now an accredited space weather operational scientist, okay? But yeah, go to Swen. If you're on Patreon, obviously you can contact me there too, or email me. You can, I think one of my emails is on YouTube, so you can contact me there as well. So yeah, join us. You'll learn a lot more than what you learn just in many courses, because I teach a whole other side of things that I don't teach in many courses, okay? So thank you for asking one of mine. I appreciate that. Okay, yes, mason jars, they rule. Okay, solar flare just now, huh? Let's go take a look. Since we're just having one, it's perfect timing. Let's take a look. Oh yeah, look at that. Nah, not very big. Let's do one day. Oh, come on, this little thing? That's a paparazzi bulb. That's not a flare. What did it get to? I'm teasing. You know I'm teasing. 1.28. Nah. And on DRAP, we'll show it, but you probably won't be able to actually, let me refresh this, because it may not show it here. Reload. Now, SUBI data comes in after X-ray flux data, so we may not see it. I don't see it. Do you guys see it? Oh, maybe. Maybe not. Do you guys see it? Might have been this little guy popping. Or maybe we just don't have the time yet. Let's see, slide this. It's a perfect example of doing this in real time. 2044 is the latest. So 2044 is where? Oh yeah, oh no, 2050. See the peak, 2050? We don't have it in the data yet. So if you go to look on Space Weather Prediction Center's websites, make sure you're checking the time if they're real near events, okay? So that you don't fool yourself into thinking you're observing something that you're not. This flare doesn't even start until 2047. Okay, right now, the latest data we have from SUBI is 2044. We have to wait three more minutes of data to come down before we even get a ghost of a chance of seeing it. Now, sometimes you can go to believe it or not, SDO's website, and they will have SDO AIA data downloaded faster than SUBI. I've noticed that recently. Most of the time, SUBI's faster, but not always. And then if we go to, whoops, hopefully I'm not making you dizzy. If we go to the DRAP model, right, we just looked at this. Right? And the flare peaked at 2050. If we load the latest, you can see the time. This will take a while, so I'm going to speed it up. Maybe if I can find my cursor. There it is. Okay, it's going to start over, but I'll go fast forward it and stop it at the flare. So DRAP model has already looked at the X-ray flux, and there's our little flare. Okay, and if you were to use that, right, 2050 was the peak. If you use that, you would say, oh, if I'm working 3 megahertz, then I'm going to have about 10 to 15 dB down, dB of signal loss, right? And if I'm using this map, I'm going to say, okay, bluish green, that's in here. Oh, well, I'm working 25 megahertz. I probably won't even notice it, because this model is saying only about, maybe 17, up to about 17 meters is noticing it. You're not getting in the yellows and in the deep greens, right? So if you're working 25 megahertz, you're not going to worry about it. You won't even notice it. Okay, see how that works? Hopefully. R1, yeah, teeny tiny R1. It still lasts for little bitty. And I'll go and I'll refresh one more time to see if SUBI got something in. Remember I talked about limb brightening? See how bright this is? It's not because these regions are this bright. If they were to rotate back into Earth view, they wouldn't be very bright. They wouldn't be any brighter than these. But you're like, ooh, they're so bright. No, no, no. It's because all the imagery is crushed right? You have all this huge area that's almost perpendicular to your view, right? If you looked out this way, these wouldn't look that bright. But because it's all folded in together, it makes these areas seem so much brighter. And that's why it always seems like, so many flares occur on the limb. No, they're occurring over the entire face over here. There's like 60 degrees that's being compressed into this tiny little ribbon. It's actually a much bigger area, right? Now let's see, see if we got any more data down. 48, ooh, we might start seeing it right at the very end. Anybody see? Let's stop at the last frame. See if anybody sees anything lighting up. Oh, there you are. Hello. See, I'll wiggle it back and forth. He's blinking on and off. Can you see? See the on, off, on, off? That little guy? There's where our flare is, but we had to wait for it, right? So, and again, using the same data products as before, still basic data products. Let's go to the solar synoptic map. Click on that, and we'll see one of these nice things. And we'll say, oh, it's region 3889. And in fact, if I can get that off, whoop, oh, come on. As I zoom in a little bit, we had about a 25% chance of getting an M-class flare from region 3889 because it's obviously got some level of complexity. Okay, and if I wanted to look at the magnetograms, then we could see where that complexity was. In fact, right now, well, it's the second most active region on the disk. The first active is still region 3883, with a 55% chance of M-class flares and a 15% chance of X-class flares. This one has got a 5% chance of X-class flares. Is it an X-flare player? It's trying to. I don't know if I would necessarily call it an X-flare player if it's only got 5%, but it's on the verge. I'd start paying attention to it at this point, especially how fast it's growing. That's another thing that at Space Weather Live you get to see is how quickly our region's growing. SWPC doesn't track that nearly, at least not openly, not on their website. So the growth, the speed at which something is growing is another really good indicator. If something is also shrinking, oftentimes, even if it's complex, if the region is shrinking or stable, not growing anymore, then we don't have more flux emergence, then oftentimes, even if it looks like it's going to have potential to go, it doesn't go. It doesn't flare big. Anyway, I hope that's useful. But look how big these coronal hole ribbons have gotten. See how big they are? Right? We even have a more polar coronal hole. Notice the layers. It gets very interesting this time in the solar cycle. It will get, this is about as complicated as it gets. Things will begin to, as the new dipole field really begins to take hold, because the dipole field has flipped, okay? We are beginning to rebuild our dipole field, and it's getting bigger. It's just now the opposite polarity. And as that continues to grow, then this will get more organized. But right now, we're basically as complicated as we can get, and as ugly as we can get. So get ready for some fun storms, and a lot of them. Okay. All right. Let's see, what time is it? 1:12. Okay, let me see where I am, because I want to go through aurora, and that'll be the last thing I'll do, is go through some aurora stuff with you guys. Okay? And yes, so I won't get to the radiation storm parts, but some of that requires extra stuff anyway, requires data products that are a bit more advanced. Okay, so speaking of aurora, here's an example of the aurora data product. This is the Ovation. It does give a 30-minute forecast. And to be totally honest, I think that 30-minute forecast really depends. They call it a 30-minute forecast, but I think it really depends upon how quick the solar wind speed is. If the speed is moving very, very quickly, they don't even have 30 minutes. Okay, but on average, it's about 30 minutes. Sometimes it's even much more than that. Sometimes it can be as much as an hour. But I don't know if they actually show it in an hour in advance. They may truncate the data. But really, it's all dependent upon what our upstream monitor is telling us. So if we have an upstream satellite monitor, which is ACE or Discover, how fast the solar wind speed is moving dictates how long it takes to get to Earth once it passes ACE and wind. And if it's moving super fast, we don't have that much time. So 30-minute forecast, take the 30 minutes with a grain of salt, because it may not be even that much time. Okay. And right now, I might as well show it because it's kind of cool. Ovation looks pretty good right now, because we've been having a very mild storm. Or if you go for Ovation, you will look for, if I can find it, aurora, 30-minute forecast. They don't even have Ovation in the name anymore. Don't know why, they should. So here is the current Ovation model, northern and southern hemispheres. And Ovation you can find everywhere, okay? You don't have to look very hard to find it. This is one version of it. You can see it because the Ovation data is given out everywhere. It's obviously going to be North America centric because SWPC is based here, right, in the United States. But you do get a view of the southern hemisphere. Other locations, I mean, is it the best for people who are not in the United States? No, absolutely not. So if you're not in North America, I wouldn't bother going here for your Ovation forecast, because there's so many other great places to go. Okay, but as you can see, it basically shows a general rise and a general fall, and sometimes you can see a view line. If you go to, they have I think an experimental, yeah, down in the experimental, don't they have it? Yeah, so they have a view line for, I don't know if it's a movie, I think it's just a snapshot, right? Yeah, just a snapshot. And they're just showing, where you can actually see a view line. Other people, when they employ the model, they actually have a view line connected to it. They'll show it. I'll show you several examples of Ovation, so please don't feel that you have to come to the Space Weather Prediction Center for your Ovation model. You really don't. During the May 10th storm, here's what they had for their view line and their forecast. As you can see, we had a lot more aurora than this, right? The views were as far south as what? The Yucatan? So I think this was off. But obviously, aurora is... actually, maybe this one isn't for the May 10th. Is it the same May 10th? This one looks better. But still, even there, they have a view line being only to about here. And aurora was viewed much more further south than that, at least from the northern hemisphere, obviously. Southern hemisphere, then the other way. So Ovation is taken with a grain of salt, right? Here's an example of one of the versions of Ovation. This is the North Pole view, and you can see aurora is a different color. This is a pretty version where it's all cleaned up. I will show you a version that is in more real time, that's not quite as clean and pretty, and you'll see why. But you can see that gorgeous auroral oval. You can see it tilt as it moves around the planet. That's because our Earth's magnetic field tilts as we rotate through it. Let me be careful how I say that. As we don't rotate through our magnetic field rotates with us, but what changes the shape of the magnetic field is the fact that the sun is blowing the solar wind at us, and so it has a certain shape. And as our magnetic field rotates with us, right, the solar wind, how it impacts Earth and impacts that magnetic field, that stays the same. So that shape stays the same, and we rotate under that shape, okay? So it's, people sometimes get confused because they're like, well, wait a minute, our North Pole, does our magnetic field move or not? Because it's changing shape underneath us, so what's going on? And it's like, well, no, our magnetic field is rigid with us, but because the shape of the magnetic cavity, right, this comet tail shape with the slingshot that slings stuff forward, that shape of the magnetic field is dictated by the sun's interaction with Earth. then as we rotate, our magnetic field is tilting with us, but that overall teardrop shape is staying still. So that's why you see the auroral oval kind of do what it does, okay? Because it's really where local midnight is. So if I play this, not magnetic midnight, well, local midnight. So as you watch it, where the auroral oval is the, it's moving too fast, where the auroral oval is the largest, or the lowest rather, dips the lowest down. And what I mean by that is the most equator word passing, which is here, which is over here now, it's rotating, right? As that's rotating, that's local midnight. So it's showing our Earth rotating through it. And what's consistent is that where midnight is, the other side is where the sun is. Okay, so that's local noon, and that's local midnight. So the auroral oval will always show you where your local midnight is and where local noon is, because the auroral oval, with this teardrop shape, will always be tilted in a sense. It'll always be strongest on the night side, okay, because of the way the whole process of solar storms unfold. Okay. But as we rotate through it, yes, our whole magnetic field is rotating with us, but the shape of that cavity and the strength of the auroral oval, where that strength resides, is dictated by the interaction with the sun. And that's why it seems to move. Okay? It's not really our magnetic field moving, it's the cavity moving. It's a complex kind of thing to explain. But hopefully that makes sense. Now, one of the popular ways, and I'm going back to Space Weather Live again, one of the popular ways to show the auroral oval is not so much on a globe, but rather a flat map. Okay? And Space Weather Live is wonderful because they do it that way. And they also have zoom-ins, and I'll show you another website that does that as well. They also have their KP index, which we'll get into next, as a nice little dial. Right now, I think it changes color. So if this were a KP9, meaning a G5 level storm, this would be completely lit up and it'd be red. Okay. Another nice thing they have is they have the hemispheric power labeled here. They don't have it labeled on the map itself. It's labeled here. So you can go from 0 to, in this case, 100, but I think they go up to 200. In the SWPC case, you will see hemispheric power labeled here. Like this was only 13.49. This is 14. Yeah. What they're talking about is the energy going through the auroral oval. So we're dissipating energy, what we call joule dissipation. And it's basically the exhaust pipe of the magnetosphere. And if you want to know more about that, see my M class, my M series of courses. You'll learn a lot about it. As well as my, what is it, the I series, the ionospheric series. You'll learn even more. But you'll understand why the energy has to be dissipated and where the energy comes from. Okay. Okay, and then I'm going to jump to ground level. I'm only showing that for the moment. That was the last bit of the ionosphere because I wanted to show you, the aurora obviously happens in the ionosphere. But some of the biggest data products that inform us about the ionosphere actually are really, they belong on the ground. And excuse me while I'm going to open my back door here to get a little air because it's awfully hot. So if you heard that, you heard my sliding glass door. So I can get some air. Okay. So we're going to start ground level stuff. And really the only thing I'm going to go into is the basic ground level stuff. Okay. So that's going to be dominated by KP. And I know there's a lot of aurora photographers going, why are you going over KP? Because I want to tell people what it is and what it isn't, right? We won't go into things like the AE index. We won't go into direct magnetometer traces in this in today's course. Why? Because this is about the basics. And I'm not training people about the different current systems in the magnetosphere. If you want to know the different current systems and how they feed the different indices, and why we use them the way we use them, please again see my M course set of courses and my I set of courses, because they will tell you what you need to know. And they'll teach you about the current systems. Okay, so I'm not sure why I put that up there. Oh, yes I do. Because if you go here, observations, because now we're dealing with observations. We are dealing with magnetospheric, magnetometers on the ground, buried in the ground typically, right? These stations that are placed all over the map. And they're not just placed willy-nilly, it's not random. There are very specific reasons why they're placed at the latitudes and the longitudes they're placed at. And that plays a role in the type of index that they then help create. But all the indices, okay, that you see are on the ground are based on magnetometer data. The biggest one, one of the most long-lived, the most long-lived, is magnetometer indices that are associated with the K index, or what we call the A indices. The K and A indices have oftentimes been used interchangeably in amateur radio operator data products, which drives me crazy, because neither of them help you. First of all, if you want to know what amateur radio operation is going to be that day, do not look at the A index, please. If you want to know the conditions that you are experiencing currently compared to the conditions of last year, fine, look at your A index, and you'll understand why in a minute. And who is trying to get a hold of me? Okay, just making sure it wasn't Mike or Jerry. Yeah, sorry, Purdue was bad, Jerry. But I'm glad you're here. Their loss is our gain. Okay, so let's take a look at the K index, right? We're going to take a look at it from an operational perspective, and then I'll dive a little bit into the science behind it. Not very much, though, because we want to keep it basic. If you go to the Space Weather Prediction Center page, as I've shown before, and I'll show again, you will see a graph that looks a lot like this. Obviously, it's not going to be pegged like this at 9. This was during the beginning of the May 10th storm. Right? You will see a scale that goes from 5 to 9. Obviously, the scale does start at 0. Okay? But what the KP index essentially is a set of 11, if not 12 magnetometers, I think 12 magnetometers that are situated around the globe at a particular range of latitudes, okay? And the reason for that is to be able to capture a global measurement of the general perturbation of our Earth's magnetic system. Now, what does that mean? Well, it means we're excluding some of the auroral effects. We don't get all the auroral effects. So if aurora lights up, you may not see very much movement on the KP scale. Okay? But then again, you're not going to be hammered forever if, how should I say this? You're not going to be so insensitive that you have to have a storm that's super strong to light up some of the more internal current systems and energize them before you get a reading, before you start seeing activity. So for people who like to use DST, for example, great, but I hope you know what you're looking at. DST is going to let you see the unfolding of a very big geomagnetic storm and let you see all the phases of it, right? Probably more intuitively than, let's say, KP would. But KP is going to react faster than DST, okay? And the reason for that, again, is because we're not having to have what we call a ring current, a massive ring current disturbance in order to move the needle. So KP is kind of like we call it a mid-latitude index, because it doesn't get all the auroral stuff at high latitudes, and it doesn't have to get the low latitude in the heart of the magnetosphere perturbations in order to register that we've got our magnetic system is moving. Okay. So in this, we typically, and it's still pretty much a stoplight chart. It used to be literally green, yellow, red. That was it. Then SWPC kind of redid their scales. So what they show you now is that anything below a KP of 5, which means anything below this, is green. Okay, fine. Do I appreciate that? No, because people at mid-latitudes, as we've already learned, people at mid-latitudes can easily see aurora when KP is 4. I think that should be where yellow is. If you want to keep KP yellow through 5, which 5 is, KP of 5 is what we call a G1 level storm. And you can see it here. So you can see their scales goes, there's a 5-point scale on the G scale. There are 5-point scales everywhere, whether it's radio blackout, whether it's a radio blackout radiation storm or a aurora, a geomagnetic storm. And I just realized I probably should have put the scales up here, but I don't know if I did that last time. But when we go into the details of it, I will go into that more. Maybe I take for granted a lot of people already know this. So G1 is KP of 5, G2 is KP of 6, G3 is KP of 7, G4 is a KP of 8 and possibly 9, and then if you get above 9, you're at a G5. Okay, so anything even peaking just above 9 is a 5. And, is a G5. And, and so all of this is a G0, but again, for aurora photographers, that's not very helpful because if you're at high latitudes, you can see aurora, you're clear down at a KP of 1 or 2. And if you're at mid-latitudes, you can see it easily at a KP of 4 if it's sustained. So there's one reason why KP isn't super helpful. Number 2 is you've got a 3-hour average. Okay? Every 3 hours, it averages all the disturbance that it's seen in the magnetometers and comes up with a measurement that goes from 0 to 9. Now, there's a plus and there's a minus, and that's kind of what you're seeing in here. So there's more gradations than that, and we'll talk a little bit more about that in a minute. And here, what SWPC shows is actually the KP values. So if you were to hover over this in real time, you will see, in this case, this would have been a 7.66 or something like that. You would see the decimal position, which would then, in case, be considered in a official vernacular. It would be considered a 7+. Okay, might even be considered an 8 minus if it were high enough. Okay, so that's all the plus and minus means when it's above. And here they're putting in 9.0, meaning 9, right at 9. Anything at like a 9 minus, which means just before 9, is still considered a G4 scale. Okay, so 3-hour averages. That's the first thing. So every 3 hours they come up with a number, but that tells you what happened the prior 3 hours. So if you get if you're waiting for your KP to advance, right, get the next number to let you know where you're at, and suddenly it does this and jumps up to here, well, that means somewhere possibly as far as 3 hours ago, the storm or whatever the disturbance is hit. So you're already 3 hours behind. And when it's something like a big G5, that's not good, right? If it's aurora, that's not good. This is historically one of the main reasons, I believe, that people thought that aurora didn't happen as far south as it does, is because KP was one of the main ways of looking for it. And oftentimes you'd look up in the sky because you're like, okay, KP's an 8, where's the aurora? Well, it happened 3 hours ago. It's gone already. So we're learning a lot more now by not just moving away from KP as aurora photographers, but also having social media, being able to alert people right away and using much more robust tools like maybe the solar wind data, right, and having experts in the loop. We're able to inform aurora photographers when these storms happen a lot faster. And now we're beginning to realize, wow, we were really off. You can see aurora when there's very little activity going on. And even more yet, as you'll learn. So the K index shown on SWPC, okay, is a great place to go to if you're looking for, a general sense of something. Okay, and if you're looking for disturbances, a general sense of disturbances. So if you're an amateur radio operator, okay, you can look at the KP. When you get to about KP of 4, that's when you start noticing real disruptions. A lot of times you don't notice anything if you're down in here. Sometimes you actually get better propagation because a little bit of storming is actually good. But it depends upon the period of, what area in the solar cycle are you. If you're in the solar minimum, disturbances like this are not good. because your solar flux is already so low that just even tiny little things can be big, big problems. But when you have a solar flux of 250, right, this kind of stuff, if you notice it, you might even notice an enhancement in propagation. Unless you're at low latitudes, right, super low latitudes, that's a different story. But so there's another way that you can use, let's say, this F10.7 flux and KP together to inform your decisions on things, because you really can't make a decision, let's say, of amateur radio propagation alone just by looking at KP. You really have to know kind of where your solar flux is as well. Okay, so this is KP, and the why it's called K, and here they're calling it planetary K, right? The P in KP is P for planetary. But you don't have to have a planetary K. You can actually have a K index at different stations. There, they take off the P. And as you can see, here's the same period, right? Here's the storm, and look how different these different stations are. You have Boulder, you have Fredericksburg. Here's the estimated KP. Okay, and of course a different color code. Of course there's a different color code. Don't ask me why. And here's College. But look how radically different they were. Now, I don't know why College was out during this period, but it was. They all have a different kind of look. Okay, so here's another reason why KP is not necessarily the best thing to do. It's a planetary average. So if you're on the night side and you're getting a lot more aurora, a lot more disturbance, then that's way different than being on the day side. Yet this just averages the whole thing out. So it's going to smear out things for you. And I'll stand out of the way if people want to take a snapshot. I just noticed this on Windy app. It was so cool that they actually just kind of made it a little bit more readable. This is the KP chart. And they have a color code that is same as the SWPC color code. I thought that was really nice that they boiled it down for you. Now, these readings, if you go somewhere else, they will be different, right? If you go to the Met Office UK, they'll have a slightly different reading. If you go to power, like the power grid, and they talk about what KP means to them, they'll have different readings, right? They'll have different stuff in the descriptions because it's really dependent upon the industry and the geographic location you're at. Okay, so just be aware of that. And so a little bit of detail here. The KP index, here is the mid-latitude regions that they use, mostly in the northern hemisphere, a couple in the southern hemisphere. There's a lot more water in the southern hemisphere, so it's kind of hard to grab lots of stations in the southern hemisphere at the right latitudes. So we have, and that's why we're not using anything here, it's because it's not at the right latitudes. Right latitudes would be down in here. Okay. And these are magnetic latitudes. That's why you're seeing this dip. So magnetic field is tilted. So to get in the right band of latitudes, we have to have, for a mid-latitude index, global index, at all sorts of different longitudes so that we have all different local times. We get a sense, a general sense of how disturbed our geomagnetic field is. Okay? Low latitudes would get the ring current, high latitudes would get the electrojet, and so a mid-latitude index gets a little bit of both, but not. Okay. So it's more sensitive than the ring current, than DST, less sensitive than AE. Okay? And this is why the KP index is used for so many different derived indices. Notice you see AP, right? Both lowercase and uppercase. The only index that's that's longer lasting than this one is the AA index, which only uses 2 stations. And that one's been going on since like 1868 or something like that. This one's been going on from 1932. So KP is with us. It's going to stay with us because we have such a long historical database of it. And it's for climatology, believe it or not. Not always necessarily for weather. A little bit for weather, but better for climatology. And AA, or in the A index, is even more for climatology. And I'll talk about why. Okay. Now, if you want to use the little a, which most people don't use, the only difference between the KP index and the little AP, right, it's a planetary index, is the scaling. See the numbers? And what that means is that the KP index, as you can see, the pluses, minuses, and zeros, right? So that's right on the money. There's a little bit more than 2. That's a little bit less than 3. Right on the money on 3. A little bit more, right? A little bit less, right on the money. Got it? That's what the plus, minus, and 0 mean. But if you notice for the AP numbers, they just go up positive. And they also go up fast. The little a P index is a linear index. KP index is much more like logarithmic. Okay? But it's still derived off of KP. It's still the same stations. And it's just a different numbering system. So that's why if you look for A indices, why are the numbers so much higher? Well, this is why. Okay? It's a linear index, so it's not squishing the dynamic range. So you're seeing a lot more activity in the low regions, and you're seeing big stuff go off scale. Right? But it expands what's going on in the lower side of things. Now, the index most people know is AP, especially you amateur radio operators, you guys use AP. All AP does is it takes the little AP data and it adds it all up into one day. Averages it for, so you have a single point for the entire day, every day. So in other words, in this particular period, September 1st through September 7th, here's what KP looked like, okay, with its numbers. AP only had this much. All of this data, all of these details are boiled down into this. Really climatology. That's what it was for. To get a record, an ideal record of what is going on that day. Was it disturbed? Was it not? Almost like a light switch. Was it really disturbed? Was it less disturbed? That's it. Day, night, doesn't matter. Just kind of how it was. Why would you use this to try to understand what your propagation is going to be for the day? First of all, it's a day behind. Secondly, it's all over the globe. And it's one number. Same thing with the F10.7 flux. It's kind of like one number. Right? You don't use these things alone. Got to put them together. And of course, AP, just so you remember, AP has to do with geomagnetic storms. This is more of something that would let you know how bad propagation will be on the night side. What you worry about more for the day side is going to be X-ray flux and F10.7. Not so much AP, or KP for that matter. This is all geomagnetic wiggles. This is radio blackouts. Okay? So when you look at it, this is going to tell you more about aurora. X-ray flux is going to tell you about what's going on the day side. Okay? So these are better used in conjunction, just like these are better used in conjunction, right? DRAP model, Ovation model, KP, AP, X-ray flux, and F10.7. Use the basics in tandem with each other. In combination, they will be so much more powerful than using them alone. And no, stop looking at AP. This is meant for space weather climatologists. The index was made for scientists to go look over years of data to understand solar cycle type effects or seasonal variations. Really slow stuff, not for your daily propagation. It's just, I think it's completely worthless for that. Now, do we have something better? Yes, we do. Some of you might recognize HPO, the indices of global activity, and GFC Potsdam. Okay. If you'd like to read about it, I talk about this in my E series of courses. I talk about it quite a bit, so I'm not going to go over it in detail. You can get the data here, but I'll show you why it's more important than KP. Basically is KP. It's just that it's not done on a 3-hour time scale. It's done on a half-an-hour time scale or even a 60-minute time scale. H means the horizontal component of the magnetic field, which is exactly the component that is being measured in KP or in K. It's always a horizontal component. And then you get P for planetary, and then you get 30 or 60. You'll see 30, HP 30, HP 60. Why? 30-minute average, 60-minute average. Sure seems a lot more usable, doesn't it? for example, here's what I show in that course. I'll show it again. Here's HP 30 for 2 days. I think, oh no, HP 60, sorry, HP 60, HP 30, okay? Just beginning on some random day in what, August of 2022. Here's the KP index for 3 days at SWPC. That was what was available at the time. I pulled these 3 plots down the same day. This is a 3-day plot, okay? This up here is a daily plot, but then you also have prior, it's like 7 days, or prior 5 days, okay, on the smaller plots. This tiny little bit, these 2 bars, are the equivalent of what you see here and the equivalent of what you see here. In KP, or in HP 60, you get, what, 6 bars? And in HP 30, you get far more, right? Because now you're not waiting 3 hours to get a bar. And what does that mean? Well, you see more variation, right? You see a bit more variation in what's going on. Here's the backups, right? I blew them up the previous days. Look at this. It's from July 31st up to August 5th. Look in the HP 30, you can see there are times where they got active conditions. That's what's in yellow, right? Even here, right, over the course of the day. This is what you get in KP. Everything highlighted in yellow there. A lot more information, right? And in this case, I only have 3 days. I'm only being shown, and this is what you get with SWPC. You only get 3 days. And then you have to go elsewhere to get your KP data. So you only get 3 days of data, whereas HP gives you a whole week. And it's much easier to pull up older dates. Excuse me, I'm choking. You can go back and look. If you go back and look for KP for this period of time that you see in yellow, there was one period where they show active. Here, look at how much they show. Even here. So a lot more detail, right? And HP 30, even more detail. Look at yellow here, right? Yellow here. You don't see any of that. All lost. So for aurora and even radio propagation, if you're stuck using the KP scale, you like that scale, it's a stoplight chart, it's easy to read, right? Doesn't take much thinking or not too intimidating. Then the HP indices, especially HP 30, can be extremely useful to you because 30 minutes, that's not a bad time scale to see changes and know whether or not you might be affected instead of having to wait 3 full hours. So here is an example of the HP 30 chart during the big May 5th or May 10th storm, right? You see yellow. Whereas before, in the KP index, it was all green, 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 and then shot straight up to red, right? Here you're actually seeing yellow. So you're actually seeing the slower build. So you see it go from an HP of, you know, a level of 1.5 to 2, if I stand on this side, a 1.5 to 2, up to a 3-ish, up to a 5-ish, and then down a little bit, then up, right? So you can actually watch, you climb slowly from a G1 to a G2 to a G3 to eventually a G4 and a G5, right? Because scale only goes to 9, right? Watch it climb again. You're seeing it going, this is later, you're seeing it go up to from a G1, G2 to G3 to a G4, in this case, with the scales going to 9, just like they do on the other. But in actuality, these scales can go higher. So we saw that slow rise up to a KP of almost 9, and then it popped up to 11. Huh. These go to 11. In this case, that's 2 louder, ain't it? Because, right, 9 is the scale where it's supposed to stop. And if you go into historical archives, for KP, 9 is as far as you get. on all those plots. So you don't really get to see the dynamics that happen above. And so this is why I say that this storm that we had was really a baby G5, is because we only hovered just barely above this. At times just barely, almost barely below it, just right around here. Whereas a lot of storms, like for instance the Halloween storms, they pegged this and went beyond a KP of 9. They were like at KP 12, 13, 15. We just don't have a measurement of that. We do now. And of course, if you go back to the raw magnetometer data, of course we have a measurement of it. We just don't have it archived in the KP plots. Okay, so people have a tendency to think, oh, G5, you get to KP9, that's it. Oh gosh, Carrington class. No, no. The magnetometers can go much further off scale. We just don't typically show that. Okay. So, cool, Jerry, thank you for putting that. Yeah. Hopefully people remember Spinal Tap. It's one of my favorite movies. Yeah, but these go to 11. All right. And now a couple last caveats here. We're almost done. Know that when we're talking about aurora and we're talking about KP and we're talking about HP, you begin to see, notice, you begin to see some details. Okay. This is an example of, I think today, right? Is this August? I mean, September? Oh, shoot. Oh, I snapped it from the website, didn't include the date. But yes, this is a current nowcast of HP that I snapped earlier today. And as you can see, you know, right now we have been storming pretty mildly, but it's up, down, up, down, up, down, up, down. And the reason for that has a lot to do with substorming, right? And that's one of the things that you need to be careful with, especially if you're an aurora chaser. Even HP 30 doesn't always capture substorming very well. But I'll tell you this much, Ovation doesn't at all, right? So if you look at aurora through an all-sky camera, this is what aurora typically looks like. Okay, this isn't even all that crazy of aurora, right? This is, you see stuff moving poleward, those are poleward boundary, PBIs, poleward boundary intensifications. You've got things moving equatorward. You've got intensifications, you've got bifurcations in this thing, you've got a westward traveling surge, you've got all sorts of omega bands and all sorts of crazy stuff that occurs with real aurora. It's very discrete, as you can see. These things come in and pulsate, they do all sorts of wild things. Look at Ovation. It's just sitting here kind of, right. It's a much smoother auroral oval. So don't be, and this is the other website, by the way. It's a great website to look at Ovation for, because you can get lots of different views. It's more European-centric because this is Austria. This is an Austrian website. This is a space weather, or basically the Austrian Space Weather Prediction Center. They've got some really good data products. We will be going back to Chris Mostel's site. He is the leader of this. We'll be going back to HelioForecast quite a few times as we go into the advanced topics. And so other things to worry about with Ovation, I mean, obviously discrete, you know, substorm intensifications, brightness, details of these surges. Ovation will not capture them. And even though they may have a viewing line like you see in this one, you will not see the up, down, up, down, up, down, nearly like what you see if you employ the magnetometers from GOES, or you look at ground-based magnetometers in the local area you're at. Because again, these are still planetary. So they're capturing the day and the night, which is much, much different than capturing a local region right under your feet. Okay. One other thing about Ovation, depending upon, and I was really grateful that this happened today. Do you see this? Did you see that for a second? There was a little, like, weird thing of aurora band. Yeah, it's an artifact. Okay, Ovation isn't perfect. See that? Right there it is. Boop, boop, boop. You'll see that from time to time. That does not mean that there's an equatorial aurora. Sometimes if you go to the NASA site, I was actually trying to go to the ISWA to get the Ovation model there at NASA, and they will have these weird vertical spikes that come down that are just like crazy, like ice picks or something coming down off the auroral oval. Artifacts of the model, not real, okay? The auroral oval above the view line is the only part of the Ovation that you should be paying attention to, irrespective if you're looking at the North Pole or the South Pole, okay? None of this is trying to mimic this stuff. So don't think that when you see those artifacts. I've seen artifacts in Aurorasaurus as well. It's all just because people are pulling down the data from Ovation Prime. I also have done that. I black them out in when I do my geochron overlays. I'm pulling down Ovation model or the Ovation model data as well. I just know to black this stuff out, so I don't let the equatorial anomalies show. But I'm grateful that they're there for us to see from time to time. They're perfect instructive tools. Just understand, right? Space weather is a growing field. The models are being updated all the time. Even Chris or someone at Helio Forecast was saying that they're in the process of updating to Ovation 2013 or something like that from the 2010 model, I believe. So these models get improvements put in all the time. So these are basic models, right? I mean, eventually we're going to have all sky cameras everywhere that are done real time, and we'll be able to see where stuff is happening. Plus, we've got so many people in social media anymore. It's only a matter of time before we get just a network that's run and that's fed annually, let's say, by a NSF grant or something like that, where we'll always have, all over the world, we'll have cameras looking at the skies. So we won't have to worry. We'll be looking at these for our, just as how well do we know the physics of what's going on, and how quickly can we make realistic models and not have to make too many approximations to make them run faster than real time. But just for now, understand Ovation is not the end-all be-all of aurora. Okay, it should give you a general opinion, but oftentimes it will underestimate how far south aurora or how far north aurora will go, and it oftentimes will, especially with fast solar wind, it will overestimate. I believe it overestimates the amount of aurora you see because I'm not sure how it handles the dynamic pressure aspect of it, but I've seen it overestimate. Okay, I think that's it. I think that is the end of the tour for today. Yes, it is. So I'll keep this here. But hopefully this helps. I know we didn't get into radiation storms. We will start doing that as we get into, as I get into the advanced stuff, and then I'll talk about NERAs and Avidos and a couple other things that we can use to get a better sense for what radiation storms are doing in and around the globe. But hopefully this gets some of the low-hanging fruit. And yeah, I guess I'm seeing what you guys have for questions. Okay, equator word is just a new word that you learned. Yes, we say poleward and equator word, because when we're talking about things, we oftentimes are talking about it relative to the globe. And you can't say up or down, right? Because in the northern hemisphere, up may be toward the pole, but in the southern hemisphere, down is toward the pole. So it gets very confusing. So it's better to say poleward or equatorward, and we'll say a poleward or equatorward motion. We also will reference things relative to magnetic local time or local time, saying pre-midnight, post-midnight, pre-dawn, post-dusk, right? Pre-noon, post-noon, stuff like that. So we sector out longitudes according to local time. That's a really unambiguous way of getting to the heart of the matter, right? And having people know where they are. So you were looking for the URL for Potsdam. Oh, you got it. Okay, cool. Thank you so much, Jerry. Appreciate that. Rad storms are rad. Yeah, it's true. And radiation storms are, in fact, a unit of dose is called a rad. One rad. I forget exactly what the unit is, but at the moment. But we use rads typically for inanimate things like aluminum and silicon for materials, but we'll use grays or even sieverts for humans, mostly grays for humans. Sieverts sometimes. As a matter of fact, I think NARAS talks about sieverts. I think they do theirs in sieverts. And I think spaceweather.com, their rads on a plane, I think they do it in grays, I think they do, or maybe they just do it in units of sea level, dose at sea level. Well, I'll try to refresh on that. So when I put together something that has all that stuff in it for the radiation storms, we'll talk about the conversions between one and the other and why the conversions aren't so easy when you go to grays, because it matters what kind of tissue you're going through. So dose is not the dose, it's not the same dose. And that's kind of the same thing as the problem that we have when we do radiation dose through silicon or radiation dose through aluminum. It's different. The tissue or the metal, the material matters because of how the particle penetrates and deposits its energy into that particular material or tissue. It's non-trivial. So that's another reason why I've left it out of the basics. I got to figure out how much I want to dive into that without making you guys go, and fall asleep on me. Anyway, okay. Question, wouldn't it be interesting to have ground-penetrating radar or pseudo-ultrasound on the sun's surface? We do have a pseudo-ultrasound on the sun's surface. It's called the helioseismology, right? We do ping the sun and listen to how it rings. And that tells us, that's the reasons why we have, we can see what active regions we can sound what active regions are lurking on the sun's far side, because we actually recognize where things damp out and where resonance is blocked and where it's ringing like a bell. And that gives us an idea when there's absorption, there might be something in the way. So we do use it to some degree. But under our ground here, I think magnetometers are really the key for us. I think part of the biggest issue that I have, and this comes to the medical side of things, is that I don't think we've paid enough attention to pulsations. Scientists have studied pulsations, and these are called PC and PI pulsations. We'll talk about them later, because they're not as critical for like things like aurora or whatever, but they're a way that the Earth rings, and it's a geomagnetic ringing of our Earth's magnetic system. And these pulsations may actually exacerbate pre-existing conditions that people have when it comes to being electromagnetically sensitive. A lot of people don't like things that wiggle really fast because they generate electric and magnetic fields inside. They induce electric and magnetic fields that are really, really teeny tiny, but they can be biologically active. And so I think as a field, if I were to say where are our holes when it comes to measuring stuff on the ground, I think our holes are not so much particles, because we have neutron monitors, which I'll talk about next time, but really understanding the pulsations. And we don't have a lot of real-time detectors on it. Magnetometers would work just fine, but you have to have people that actually want to take the time to detrend it and pull out those pulsations of different styles and natures and put them together in a database. And it's just not a big enough, at least from my experience, in the operational world, it's just not a big enough field of study. It is in academia, but not so much in operations. So we do have data, it's just not being mined as well as it needs to be, if that makes sense, hopefully. Okay. Let's see, I saw someone say something confused. Uh-oh, I don't like that. Let me know if I can help explain. And another question just went by too quickly, I couldn't see it. You'll try this useful information in my increasingly electrolyzed brain. Yeah, right. And I remember, I forget who asked me, Spock's daughter might have been, you had asked me about cadence. And I went through, especially with nowcasting for HP, right? We're talking about cadences, 30 minutes. Right, the SUBI has a faster cadence when it comes to imagery than does SDO, AIA, but it's at the cost of resolution. So you have a lot more data, a lot more imagery, if I recall, and I think SUBI shows it, but a lot of times with like the SDO website, you can get higher cadence, but it's not what is available without you actually going in and downloading movies and requesting cadence at a specific speed and that type of thing. But those are typically in the order of seconds to minutes. I'm trying to think, what other cadence do we have? Ovation is, I think, 15 minutes, half an hour? 5 minutes. 5 minutes, but they don't always update it in 5 minutes. DRAP is 1 minute. I think it's 1 minute. Which I just love DRAP. It's a great thing. Hopefully that answers a lot of those questions about cadence, but we'll get into more things about cadence. The critical part, though, is when you look at everything being updated on the SWPC site, or any site you go to where they're pulling down data, right, from NASA, NOAA, and these other places, always compare your time stamps. Always make sure your time stamps are the same, because the data isn't always being pulled down at the same rate. So if you're not careful, you can think something is occurring right now, and one of your data products is up to date and up to time, and another data product hasn't gotten there yet. And that can be extremely frustrating. One of the things that languishes way too long is coronagraphs, right? And so we have new coronagraph data that's coming. SWPC is still testing it out. I just learned from the M2M folks that they do not have access to it, which makes me go, come on, at least give the NASA M2M folks something, because they're so critical in the loop for astronaut safety. But hopefully SWPC will start releasing those data products, the coronagraph data, and it will catch up faster than SOHO LASCO. SOHO LASCO, they do all sorts of campaign events. They're still an academic resource, so even though we use them for operations, we do have to bow to the PI who contracts out LASCO for use for the scientific community. I mean, they do need to stay funded, right, to keep themselves up there and keep themselves healthy. So, soon we'll get access to the chronograph on SOHO, on GOES, and we'll have a dedicated chronograph for operations, which will be great, right? And so you'll see that better. But just until then, be aware that chronograph data on LASCO is slow to catch up, okay? Okay. I heard volcanoes, earthquakes, and tsunamis can cause ringing to occur around a planet too. Yes, especially in the Schumann resonances in the neutral atmosphere. But it also, as I talked about even in a briefing, I think it was a forecast briefing I did, during the Tonga explosion, for example, we watched that volcano go all the way up, and I've made it, I've done the analogy that it's kind of like dropping a stone in the water, but instead of it being a stone in the water, imagine the water is your ionosphere. Right, it's the surface of the ionosphere, and you're dropping a stone and it's going up, and it makes this big splash and the ripple moving out. That's our ionosphere rippling out, and you get these what we call trans-ionospheric disturbances that move out, just like you saw the ripple in the water when you drop that stone in. We saw the Tonga explosion not just ring the neutral atmosphere, but ring the ionosphere and then ring even out into the magnetosphere. We actually were able to measure some of the disturbances we saw from that explosion. So yes, all sorts of terrestrial weather and space weather are coupled, absolutely coupled. We just don't understand that coupling all that well yet. And the reason why is because we can't fly satellites in that region. We do sounding rockets, and their mission lasts, 30 seconds, maybe a minute if we're lucky. But there's just too much drag in that region for us, and that's right at the E to the F region, right in there. And that's just right at the low end. We're talking about 100 kilometers to 200, 300 kilometers, all in that region. That is just the wrong place for satellites to fly. That's why Elon's birds fell out of the sky. They were flying in that regime, in that area that we often call the ignoro-sphere. And the reason for that is because we can't fly long-standing missions there because the dang birds get pulled down. So we're learning a lot more about our own coupling, our own atmosphere by flying birds at Mars, because their atmosphere is so much more tenuous. So we can actually learn more about it because we can fly satellites in that regime. It's crazy. We have to go to another planet to learn more about our own. But we're getting there. We're getting there. So who owns Lizard? LASP does in Colorado. And they're connected very closely to the University of Colorado and also with SWPC, the Space Weather Prediction Center. In Boulder, Colorado, there's a whole bunch of really space weather-centric brains and meteorologists as well, because you have UCAR and NCAR there as well. So it's a real hub for a lot of that operational data. You're welcome. Okay, let's see. Any other questions, guys? Hello, Dr. Tam of the Scope. Hope you're doing well. Yes, thank you. The earth is loud and vibrations here and there in the body. Friendly greetings from Germany. Oh, good. I'm so glad you've enjoyed this, and hopefully you get something out of it in terms of you know, whatever science or endeavor you're working on. Hi guys, hi. Mason jars. Yes, more about mason jars. Elon's birds makes it difficult to see my stars. Yeah, part of that is to do with the atomic oxygen up there. In low Earth orbit, we have a lot of atomic oxygen, and that it's very reactive. Oxygen doesn't like to be stripped into an ion. It scavenges electrons a lot, and so a lot of times what ends up happening is that it changes paints, and you can even, and I know some fun stories that I could tell, but the paints even on birds that the Starlink crew are trying to paint their birds dark colors, like a dark black that's matte, that's, you know, not glinty. They're trying hard to find a paint that will withstand the atomic oxygen environment, because what happens is that in certain cases, depending upon what the chemistry is, you actually have chemistry going on up there. And so your matte paint may suddenly get reduced and turn into a shiny metal coating, either because of atomic oxygen or because of the radiation depositing of electrons into the material. There's all sorts of cool stuff that goes on. Or you can get the shredding of the coatings, really thin coatings, thermal paints, optical coatings, all of that stuff. When they're super, super thin like that, they don't have a good time in space, because the low energy particle environment really causes their doses to be very high, the radiation doses to be high. So that's a real problem for them. So it's not easy. And so give them time. The paints will get better to keep things matte, but the older the birds are, likely the more shiny they are. That's my guess, at least right now. I'm not involved. I haven't been involved with aerospace stuff for several years now, so I will just leave it at that. It's not a headache I wanted to have to deal with, but I know a bit more about it than I care to admit. Let me say that. Okay. So do I think a full pole shift will affect satellites? Absolutely. Oh my goodness, it'll be a fun time. Space weather environment's going to change. I don't even know whether we're going to have stable radiation belts, right? The big thing that I worry about, I don't worry about currents in the ground. I don't worry about our power grids. I don't worry about us with geomagnetic storms. That's easy. We actually get a break when it comes to that. What I worry about is particle precipitation, because if we go to a multipolar Earth, even for, you know, a short couple hundred years, now we got a lot more particles precipitating, and more energetic particles precipitating in multiple places down at mid-latitudes, that type of thing. Aviation is going to be fun. I think passengers will get higher doses of radiation, so we'll have to make new laws regarding that and get new safety regulations. This is many years in the future, obviously, but I do believe it's probably coming. I think satellite designers are going to have a hell of a time because the LEO environment may change dramatically. Astronauts in space, it's going to change dramatically. And we're just beginning to try to study like the quadrupole field and what that is going to be like. Will it be able to stand off solar storms? Absolutely. We're not worried about our atmosphere being stripped off, none of that. So all the crazy things that people talk about on YouTube and elsewhere about the pole shift, they're looking over here and they're all so scared about this 800-pound gorilla, and they're missing the fact that there's a 900-pound gorilla right behind them, ready to tackle them. They're not paying attention to the things that really need to be, figured out. And that has a lot more to do with our space assets and aviation than it has to do with the geomagnetic electric grids and whether or not we're going to see aurora down at the equator. We already do. I mean, So I think that's going to come as things begin to change, but I think likely the industry is going to push that. And so the money has to pivot. The money for the research has to pivot over to the places where it's needed. And that has yet to happen because we haven't seen big enough changes yet in our infrastructures, and how we look at things. We're able to still do correction factors on, our current magnetospheric models and where compasses are, and we haven't seen significant changes in particle precipitation yet that is affecting avionics and stuff like that yet. So the money hasn't pivoted yet to that area of research. But it is trickling. So we are seeing some analyses that have been done. I'm seeing more pop up all the time, and I think we'll continue to see that over the next, definitely the next solar cycle. I think, especially if the solar cycle gets to be even bigger, which it could. That'll be a much bigger topic of discussion during the next solar cycle, okay, during next solar max in about 10 years or so. So come back in 10 years. But, don't worry about what the crazies are saying on YouTube. They're not looking in the right areas, to be totally honest. Okay. Hope that helps anyway. Could I talk about the Earth polar wind measured by Goddard? Are you talking, when you say polar wind, you've got to be talking about terrestrial, right? And I can look it up, but it's not something I know a lot about right now. I'm not a terrestrial meteorologist. The neutral atmosphere is not my forte. I wish I knew more, and I will eventually learn more. I just can't right now, and so I don't want to try to speculate on any of that stuff because it's not my field of expertise, right? But if, Antonio, if you could tell me a bit more what you mean by the polar wind and whether or not it's a terrestrial measure, like the polar vortex, that type of thing. Because if you're talking about the polar vortex, then yes, it is affected by space weather. Absolutely is. We've seen that, in fact, in Nathaniel Frizzell's graduate thesis work. Nathaniel, who works at HamSci, who's a creator of HamSci, all of his graduate thesis work was on the polar vortex and how space weather events, namely geomagnetic storms, affected it. And we see that too. There's a paper done not that long ago by some people in Finland. They did a study of how Finnish houses used less heat, used their heaters less, and used less electricity when big geomagnetic storms occur, because the aurora actually heats the upper atmosphere and that trickles down to them. So it ended up taking, being a heater from the sky. And so that was actually measurable by their, just by looking at the data of their electric grid infrastructure. I think that's fascinating. But it's understandable. The aurora, occurs, and if it gets stronger, all of it, it's always convecting down earthward, or equatorward anyway. But there's no reason why it wouldn't end up affecting the neutral atmosphere to the point where it might cause people to dial down their heaters just a little bit. I just find that just tickles me. But yeah, so there are studies on that stuff, if that's what you mean. Okay, is the space industry preparing for these radiation changes? About as slow as a brontosaurus turns, if that answers your question. So some people, yeah, but they've got to be space weather savvy, and most aren't. So that's a complex answer. But let's say people are beginning to pivot, but it's going to be very slow turn. Okay. You're welcome, Jerry. Yes, I know, we're wrapping up. So glad. It's outstanding information. I'm so glad you enjoyed it. If a CME impacts North America and is in daylight, is the AL index a good indicator or predictor of what to expect at nightfall? Again, the AL index, right? You're talking about the AL and AU, right? The lower envelope and the upper envelope. These are basically talking about the eastward and the westward electrojet. So it depends upon where you are. If you are at higher latitudes, then yes, it might, right? But it doesn't. You really need to look at, the nice thing about the AE indices is that they are planetary. So they're going to smear out things. Obviously, they're not as good as your local magnetometer stations, but for a quick look, they're fine. And because they are planetary, they're going to give you an impression of how active the auroral oval is in the, either in the eastward or in the westward electrojet. I think the westward electrojet is the one that's probably the lower, right? Because westward is below the eastward. One goes eastward and it's above, and the westward one goes below it. So you're looking at AL in that case. I would look at AE. I would look at the difference between the two. That's why I like AE. Rule of thumb is 500. If it's 500 or larger, you're good in good substorm territory. But obviously, there are even better tools if you're willing to dive a little bit deeper into the details. And that's something we'll get into when we talk about the advanced stuff. Okay, So hopefully that helps, Craig. Who is the belly button that needs to meet with that 900-pound wake-up call? Yeah. Yeah, there's a few people. I'll stay quiet. Yeah. I think they know who they are. Okay, Leon, I am the person with the medical medal in the head and on the skull. Yeah, so sorry. The thing with the birds, you're shiny, but you're young and a beautiful soul. Thank you. Yeah, sorry, Leon, you probably hate geomagnetic storms with a passion. You might actually even be susceptible during pulsations, PC and PI pulsations. Because anything electromagnetic is just going to drive you nuts, right? Probably give you pain, general malaise, headaches, migraines. So sorry. Hope you're okay. Just know we'll get through Solar Max, and then at least you'll be able to plan for big geomagnetic storms, because when the big fast streams take over, then it's every 27 days, and you'll know just to hunker down or not put anything on your schedule for the 2 or 3 days that we're dealing with it, and then you're good for another at least 2 weeks, if not a full month. So it's the best I can do for you. Truly love these mini courses, thank you. Solar disk looks really pretty and regular optical with all the spots. Yeah, I bet it does. Like a pockmarked Dalmatian. Yeah, I bet. Finnish are the happiest people in the world, and now I know why. Yes, they get to be heated by aurora. It doesn't suck, does it? Okay. Yes, I mentioned that the one done in Finland, right? Okay, guys. Koku Bunny, yeah, of course I know Ben Davidson. Of course I do. My opinion of him is mixed, as it always is. I am very grateful that he does space weather and that he's raising awareness of space weather, but he is not formally trained. And some of the speculation that he does is unphysical. Let me just put it that way. He makes connections that are not physically plausible. He also forgets to put certain things in context. So while I appreciate what he does to raise awareness in space weather, I appreciate that very much. There are certain aspects where I think what he does is sensational, and I think he knows that. A lot of my colleagues have reached out to Ben and tried to get him to be a bit more realistic in his expectations, and he just shuts them all down. So I think he likes what he does and how he does it, and so what we have to do with just like with everybody else on the planet, you take the good with the bad, right? He excites a lot of fringe scientists, and I really appreciate that, because fringe science is something that is super important to our field, just like mainstream science is important. And I've said it probably so many times, I'm such a broken record, right? It's like two hands shaking, right? The left hand and the right hand. Fringe science, or let me say it this way, mainstream science keeps fringe science grounded, but fringe science gives mainstream science wings. And I will say that until the day I die. I think it's important to have both. And so because he does a lot in inspiring fringe scientists to go on these quests for the truth, I will always appreciate that work. What I don't appreciate is when he attacks mainstream scientists for the work that we do. But that's his way, and people choose their own paths. So I'll leave it at that. Hopefully that makes enough sense, and you can handle that as a diplomatic response to your question. Okay, we're beginning to, so as we move off on to gamma rays, that's a different story. And no, gamma rays aren't going through everything. I think you're talking neutrinos, because gamma rays are actually absorbed by our atmosphere. We have an atmospheric window, and gamma rays are not allowed in. So gamma rays are only observed up in space. So we don't have to protect ourselves from gamma rays, okay? There are other aspects of cosmic ray showers, and we'll talk about them when I talk about radiation storms, okay? But it's a little bit more of an advanced topic. That's why, again, I'm not including it here. So come to our next class, and I likely will be talking about them then, okay? All right, guys, we just had another flare? Cool. I'll take a look after we get off here. All right, guys. Always enjoy a drink from a fire hose. Thank you, Edward. You obviously have been here before. You know that phrase. Yes, drinking from a fire hose. Hopefully this one wasn't too bad. Hopefully not too bad. I've had much more intense courses than this, so I appreciate you sticking through to the end. Much appreciated. All right. Yeah, I agree, Spirit. You know, we need to be more diplomatic with one another. It gets too personal, and that's just silly. Okay, everybody has their place. We're all here for a reason. Nick, hi, Nick. Good to see you. Things look like they're pretty active, and good to see a lot of familiar faces around. Yeah, I agree, including yours. I'd love to see it. Look out, Nick. I'm going to be sending out a new VIP doodle poll here soon, so if you want to join us, we'd love to see you. Okay, guys, Stella Q, you're very welcome. Absolutely. You know, and it's the truth. I mean, I feel that way about Ben. So I don't care what he thinks about me. I know what he thinks about me. It's okay. It's okay. He can think about me any way he wants. You're very welcome, Randall. Okay, guys. Yeah, I know. Let's not talk about AI. That's a crazy one right there. Do I think science today has become too diplomatic, interfering with scientific results? Certain areas, absolutely. Other areas, not at all. I can think of people who are outrageous. Come to a scientific conference sometimes, and you will see them yelling at each other in a room. I mean, it can be very crazy. Go talk to the Substorm crowd in space weather, for example, and they do everything but pelt each other with olives. It's pretty crazy. So the answer is yes and no, as you'd expect it to be. It really depends upon the field. Okay, guys, thank you so much. You're only here for coffee and smoke, so you have to get them in the side room. Go to the green room and you'll see them. Just kidding. Okay, guys, thanks so much for a great class. Hope you enjoyed it. And the next one, we'll start diving into more advanced topics, okay?